Yes.
Bismillah ar-Rahman ar-Rahim. Vice Presidents, Deans, distinguished guests, and esteemed speakers. Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. My name is Hadil Suleiman. I am a senior chemical engineering student here at KFUPM. And it is my honor to serve as the Master of Ceremonies today, along with my co-MCs.
Good morning, everyone. My name is Judy Dewi, and I'm a sophomore chemical engineering here at KFUPM.
And I'm Balqis Sudan, also a chemical engineering student here at KFUPM. And as we say in Arabic, أهلا وسهلا بكم جميعا. A heartfelt welcome to you all.
It is our great pleasure to welcome you all to the opening ceremony on behalf of the organizing committee of the Saudi chapter of the American Chemical Society International Conference. Before we begin, allow me to share a brief note. In case of emergencies, God forbid, please note that there are 2 exit doors on the side of the hall and 2 at the back.
Well, ladies and gentlemen, today we're not just hosting the Saudi chapter ACS conference for the first time here at KFUPM or in the whole kingdom. We are witnessing the chemistry of change, where every discovery begins with a question, every transformation begins with courage. Same courage that built this university 62 years ago, and it's the same courage leading it today into being the first university in the whole Arab world and the 67th ranked globally with a diverse community in new worlds of material science, energy transition, and innovation that speaks every language.
This milestone reflects Saudi Arabia's continuous progress in research, science, and innovation, aligned with Saudi Arabia 2030 vision. Today, we bring together brilliant minds from across the globe on an exceptional platform that unites Nobel laureates, King Faisal Award winners, and leading researchers to share their expertise under the conference theme, Chemical Innovations for Sustainable Future Industries.
To begin our ceremony, we're honored to welcome a leader whose efforts continue to embrace progress across the College of Chemicals and Materials at KFUPM. Please join me in welcoming the chairman of the organizing committee, Dr. Hassan Ba'aqil, to give a brief about the conference.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, everyone. On behalf of the organizing committee, I welcome you to the first Saudi chapter American Chemical Society International Conference. I'd like to start by confessing that this conference is long overdue. KFUPM has been in the forefront of chemicals and materials in the region since its inception in the 60s. So chemicals and chemistry is in our DNA. We always envisaged at the College of Chemicals and Materials that we become the destination for education, knowledge, innovation, networking in the chemicals domain. And we are well positioned for this role. First, we have the legacy at KFUPM in the chemicals and chemistry domain. We are also surrounded by an excellent ecosystem, including companies, chemical companies, engineering services companies, research centers around us. All that ecosystem is around KFUPM. Third, we have exceptional growing capabilities at KFUPM. A few months ago, we have commenced a new center on Petroleum Conversion Research Center that is one of its kind in scaling up chemical processes and chemistry research. I'd like to start by thanking the different committees that made this a reality. I'd like to start by the advisory committee, thanking Dr. Ali Sheikhi for his advisory role, and also thanking all the organizing committees behind the scene. This conference covers a number of themes and a number of topics that runs parallel presentations in the following topics. The first is sustainable chemical processes, energy conversion and storage, petrochemicals and value-added products, environmental chemistry and engineering, and finally, AI and chemistry education and industry. Finally is biochemical technology for industry. To give you a glance on the conference, the number of keynote speakers we have in this conference is around 25. We have more than 4 workshops. We have 4 workshops. We have more than 1,500 participants, 2 discussion panels, and 1 exhibition that you will see in a minute. The total number of abstracts we received in the conference is 325. That resulted in 91 oral presentations, 265 poster presentations. We have participants from more than 30 nationalities across the world, and our keynote speakers also come from across the world and with different backgrounds. We have Nobel laureates, we have King Faisal Award winners, and pioneers in their fields. I'd like to conclude by thanking our sponsors who helped in sponsoring and funding this conference, and also all our exhibitors and strategic partners. I wish you a fruitful and enjoyable event. Thank you for coming, and enjoy the rest of the conference. Thank you.
Thank you, Dr. Hassan, for your inspiring words and valuable message. Next, we are honored to welcome a distinguished global figure in chemistry, a visionary leader representing one of the world's largest and most influential scientific societies. Please join me in welcoming Dr. Dorothy Phillips, President of the American Chemical Society, who is joining us through a special recorded message to share her remarks.
Hello, everyone. I am Dorothy Phillips, 2025 President of the American Chemical Society. On behalf of the ACS Global Community, I am delighted to extend my warm personal greetings to all of you attending the Chemical Innovations for Sustainable Future Industries Conference 2025, hosted by the Saudi Arabia chapter of the American Chemical Society. As President of the world's largest scientific society, I am proud to represent over 230,000 members globally across 190 countries. Closer to our meeting today, ACS has more than 3,000 people in our member community, alongside 10 international chapters and 39 student chapters across the Middle East and North Africa. Today, I am so pleased to see attendees from around the globe come together to join this conference, share science, and connect with one another. One of my goals as ACS President is to work with our members outside of the United States to strengthen our professional and student chapters and build cohesive ACS networks like the one located here in Saudi Arabia. The ACS Saudi chapter, the first ACS International Chemical Sciences chapter established outside the United States, has become a leading platform promoting chemistry, innovation, and sustainability across the kingdom in alignment with the Saudi Vision 2030. Through national conferences, workshops, and student competitions such as Chemathon, the chapter has fostered collaboration among academia, industry, and government to advance green chemistry, renewable energy, and circular materials initiatives. The chapter has also strengthened international scientific partnerships, connecting Saudi researchers with global ACS communities, supporting women in STEM, and organizing outreach activities that promote public understanding of chemistry's role in sustainability. The ACS Saudi chapter, in collaboration with the American Chemical Society, has organized several international conferences outside the kingdom. For the first time, the chapter is hosting its flagship event within Saudi Arabia in partnership with King Fahd University of Petroleum and Minerals, KFUPM. The ACS Saudi Conference on Sustainability, AI, and Chemical Education brought together more than 300 speakers and hundreds of students and professionals, highlighting the kingdom's growing leadership in sustainable chemical innovation, advanced research, and education. The ACS recognizes your role in advancing science through our shared mission to advance scientific knowledge, empower a global community, and champion scientific integrity. All your many friends and colleagues in the American Chemical Society look forward to continuing our strong working relationship. I wish you all the very best for a successful conference and beyond. Thank you.
Okay, sorry. What a great message from Dr. Dorothy. Truly insightful and inspiring, highlighting the vital role of chemistry in shaping a sustainable future. Now, we move on a patronage speech on behalf of KFUPM President, delivered by a visionary leader, the Vice President of Research and Innovation at KFUPM. Please join me in welcoming Dr. Ali Sheikhi to the stage.
بسم الله الرحمن الرحيم الحمد لله رب العالمين الصلاة والسلام على أشرف الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين أما بعد. Distinguished guests and speakers, esteemed colleagues, ladies and gentlemen, Assalamu alaikum wa rahmatullahi wa barakatuh, and very good morning to everyone. First of all, I'd like to convey to you the greeting of the President of King Fahd University of Petroleum and Mineral, Dr. Muhammad al-Saggaf, and his best wishes for informative and fruitful conference. I also extend my heartfelt appreciation to all the speakers coming from around the world. We have really distinguished speakers coming from around the world. And also I'd like to thank the College of Chemical and Material, the Department of Chemistry in particular, KICS, which is KFUPM Institute for Knowledge Exchange, all the organizing committee, the sponsors, exhibitors, and the American Chemical Society, Saudi chapter, for all their dedication to bring this conference into light. It's my really great honor to welcome you all to the American Chemical Society Saudi chapter International Conference 2025, hosted here at King Fahd University of Petroleum and Mineral, under the visionary leadership of our university and the guiding spirit of Saudi Vision 2030, the conference stands as a symbol of our science and innovation drives progress. It reflects our national ambition to diversify our economy, empower our youth, and place knowledge, technology, and sustainability at the very heart of our nation growth. Since 2020, King Fahd University of Petroleum and Mineral has embarked on an amazing transformation journey, aligning our academic and research mission with the kingdom's economic diversification goals by developing economy creating talent that will lead these future sector of the kingdom. In research also, KFUBM has launched over 24 new thematic centers dedicated in solving real-world challenges through innovation and interdisciplinary collaboration. Through strong partnership with industry, we are pushing our work toward higher technology readiness levels, ensuring that every discovery moves from the lab to life. Today, KFUBM stands among the top 67 universities in the world based on QS latest ranking. Also, we were ranked #1 in the Arab and Middle East region for 3 years consecutively. But beyond rankings, what truly defines us is impact, our ability to transform ideas into solutions and solutions into progress. To amplify that impact, KFUBM really did many changes, transformation, and activity. I'll focus just on few that is related to chemical and chemistry in particular in relation to this conference. One of them is we created a new college. We call it the College of Chemicals and Material. And it's led now by Dr. Hassan Baagil with his really amazing and leadership effort and work in this college. Bringing together chemical engineering and chemistry under one college. And also we have established and added to this college 2 new departments, one in bioengineering and one in material science and engineering to this college to make it one powerhouse college of innovation, because we believe that science and engineering are inseparable in shaping our future. Our new research centers, as I mentioned, we have many, but the one that is closely related to chemical and chemistry, for example, I hope the others will not get upset if I did not mention their centers, but in particular, advanced material, membranes and water security, refining and advanced chemicals, hydrogen technology and carbon capture, and also our newly established upscaling facility, the Petroleum Conversion Research Center. All are united with, of course, all the other centers, whether in AI or other related, CIBR as well, the Integrative Petroleum Research Center as well. They are all united under a shared purpose to meet our grand challenges for 2030. I'll mention just few, some of our grand challenges, although we launched recently, or actually a year ago, our research strategy comprising of more than 40 grand challenges and over 80 innovation goals. I'll just mention few that is related to chemical and chemistry. producing hydrogen at less than $0.50 per kilogram, developing multifunctional catalysts that convert crude oil to chemicals in a single step, reducing desalination costs by 50%, cutting carbon emission in the kingdom by 30%, increasing waste reuse to 30%, and producing graphene from petroleum coke. So these are not just scientific ambitions, these are some of our national commitments to the sustainable future we envision. Let me just go back to the conference. So the theme of this conference, Chemistry Innovation for Sustainable Future Industry, perfectly reflects that vision. Over the coming days, we will explore the artificial intelligence, advanced material, digital technologies, and green chemistry in a way to reshape the industry, education, and the world around us. Scientists, researchers, educators, policymakers, and industry leaders from across the globe are gathered here, united by one shared purpose to advance chemistry in the service of humanity and the environment as well. But as we celebrate his discovery, we must also look inward and ask, are we preparing the future leader, our student, especially in the field of chemistry and chemical, for the future? This is what the university should do, should foresee the future and prepare for it from now. Today, I believe it is time to reimagine how we teach and learn chemistry. The chemistry curriculum of yesterday, I think, is no longer enough for the challenges of tomorrow. We must integrate sustainability, digital intelligence, entrepreneurship, and ethics into every classroom and every laboratory. Chemistry is not only about what the world is made of, it's about what the world can become when we change the way we teach, learn, and imagine it. Let's dare to change our chemistry so that the next generation doesn't just study science, but shapes the future through it. Thank you very much, and I wish you all a memorable, inspiring, and world-changing conference. Assalamu alaikum wa rahmatullahi wa barakatuh.
Thank you, Dr. Ali, for your inspiring remarks. We kindly ask you to remain on stage as we take a moment to recognize and honor our valued sponsors, whose support also extends to encourage programs such as the Chemathon, which celebrates excellence in undergraduate research, competition, and innovation. Ladies and gentlemen, please join me in welcoming our valued sponsors, starting by Lab Technologies. Bayoni. الأداء. Fine Chemical Society. Sir Ali, for your cooperation. Following that, we'll have a photo shoot with all attendees to celebrate this special occasion. Kindly stand up for the photo shoot. Thank you, everyone. We will now take a short break to visit the exhibition opening. The conference will resume shortly after 30 minutes. Thank you, and please enjoy your break.
انزل بقى في خير.
Everyone please come inside the hall. Everyone please come inside the hall. Session is going to be started soon.
Assalamu alaikum and welcome back everyone. We hope you had a refreshing break. And now we are deeply honored to begin our first keynote session with Professor Morten Meldal, a Nobel laureate in chemistry. His pioneering contributions to click chemistry have reshaped modern science and continues to inspire others around the world. Please join me in welcoming Professor Morten Meldal to the stage.
Hello everyone, it's a real pleasure to be here today. I'm very honored to be invited by the Saudi chapter of the ACS to give this presentation. So in 2022 I got a phone call, a life-changing phone call from Stockholm, and I took the phone and it was the Nobel Committee, and they told me that I would be sharing that year's Nobel Prize with Caroline Bertozzi and Barry Sharpless, two very good friends of mine from the US. When you get a Nobel Prize, you're supposed to have an opinion about everything. I don't know about everything, but I do know that chemistry is everything, and this is a mantra I've had for the last 3 years, and it's also now the mantra for the ACS meeting in chemistry in the US, so I'm very proud of that. And chemistry is everything has a lot of implications. So actually, the complexity of life, everything of that origin in the properties of the atoms. The atoms are much more complex than we as chemists tend to lend to them. We think of chemistry as being a simplified thing on 2 dimensions, but the chemistry world is really, really complex. The orbitals are overlapping in the same space. They are much more complex than what we usually draw on a piece of paper. And they together comes to a complexity that leads to life just with 16 different atoms out of the elemental table. That's quite incredible. So chemistry is everything, and because chemistry is everything, I also advocate for education, in order to meet the challenges that we have right now, in order to educate our young people to be able to handle the situation that we have created for them. This is why sustainability is at the top of the agenda everywhere today, and I think that education in this area is really, really important from a chemical standpoint, understanding the big picture of chemistry, what it is, and then engineering fits into that in all sorts of ways to get the application solutions out of it. But in order to understand what is really that we are looking at, in particular with the life processes, there are 5 different functions in life. Molecular recognition, every single event, every single thought you might have, every single action you take is initiated by a range of molecular recognition events. Without molecular recognition, there was nothing. And then understanding that molecular recognition is extremely important. Transformation, molecular transformation, what enzymes does is an extremely important event. Then signaling into the center of the cell to the nuclei to get expression of particular proteins in response to external stimuli. Another very important function. Molecular transport across the membrane. The membrane is like a concrete layer around the cell to protect it from the environment. And we need things to come in and out of that. And the only way to do that is to be able to open the doors into the cell. And then molecular replication, of course, life requires that it can repeat itself again and again and again. We have not been working much with molecular replication, but the other 4 items is very much addressed in the talk I have today. And through click chemistry, in my opinion, one of the best additions to chemistry in a long time. So we built at the Carlsberg Laboratory, we built a platform to handle all these questions. And the platform is based on combinatorial chemistry, where we can synthesize millions of molecules in a short period of time using the exponential, the exponential growth of molecules in the combinatorial scenario. You can see up here in the right corner. And then we can make molecules, 1 molecule on each little particle. And then we can pick out the active ones, like the blue ones you see here. We can resynthesize the molecules and inject them into a mouse. In this case, we are looking at a mouse with arthritis in 1 foot. And we have isolated a substrate that is very specific for MMP13 protein that is active during inflammation. And we can see that activity in a time course in the mouse foot. We can also grow cells on the surface of our microparticles, our beads. And here we see a monolayer of cells that respond to a stimuli from a compound on 1 bead. And this is a G-coupled protein receptor signaling that we are looking at. And we can then analyze the compound on that bead, which is active, and get a new G-code protein receptor agonist. And we also can encode, so we have an encoding system like a barcode on each bead, and we can then encode for the molecules that we are synthesizing and analyzing. So this is a platform technology we implemented at the Carlsberg laboratory. During this period, we also worked on the chemistries. So a lot of organic chemistries was tested on solid support together with peptides in order to merge the world of peptide and organic chemistry and make complex molecules. So here's one of these attempts. We are using acetoacid chlorides, very small protecting group for the amine, very high activation of the carboxylic acid, and we can synthesize peptides that can only be synthesized in this way because of steric hindrance. And this led to us thinking maybe this is a good way to do chemistry in general. And I asked Christian Tornø to take an alkyne. So an alkyne is a carbon nucleophile if we deprotonate it, and we can do that in the presence of copper 1. Then we have a nucleophile that can react with the acid chloride. That's what we thought, because if we could do that, we could use cycloaddition reactions, Diels-Alder chemistry, to attach large groups to the side chain of a peptide. That would be very interesting, and as you know, today Ozempic is a blockbuster drug, and this is what we had in mind with this chemistry. But it was not successful. So Christian tried this for several months, and then he came to me and said, Professor Mildal, I think it's time maybe I start working at Novo Nordisk instead of here. I think I should find some other job. And I said, and then let's look at what you have done. And we took all the data and we went through them. And this is sort of a moment where you have a serendipitous discovery. We found that we get this compound instead, even in the presence of the very active acid chloride. So I told Christian that this is a unique reaction and we have to investigate it in more detail. And he did that. He investigated the compatibility of this reaction with all the amino acids and with sugars. And then he presented that at the American Peptide Symposium in San Diego in 2001. And this is Christian on the right side of this image. Well, what is it then, the click chemistry? Here's an alkyne. It's a very electron-rich molecule, has a lot of electrons in pi orbitals. And now we see a copper 1 plus coming in from the side, and it's attaching itself to this electron density. That acidifies the alkyne because of the extraction of electron density. So now the proton falls off and the copper can take its place. There's not a lot of difference from before. But a friend of this copper 1 atom comes in, sits on the pi electrons, and then they peel it off like that to get into the goodies inside. So this is the LUMO, or empty orbitals, that are created by this copper attachment. So the LUMO here fortunately fits exactly with the HOMO, the electron-rich orbitals of the A side, both in terms of phase and in terms of geometry. So we form two new bonds, and this is a metallocycle, which first loses one copper atom, then it loses the second copper atom, and we have an extremely selective attachment of one functionality to another functionality. This is good for attaching a phenyl group to a methyl group, and that's not very exciting. But the fact is, this can be used for so many different things. We can make robot molecules, we can ligate onto strips of surfaces, we can do stapling of structure, we can do polymer synthesis, we can use it for cell-penetrating peptides and affinity activity profiling, and then for green drug synthesis, because click chemistry is characterized by being completely water compatible. So this is a chemist's view of an antibody, something that you can actually synthesize in the laboratory, and something which has function. So the function we are looking at here is molecular recognition. We want to be able to design molecular recognition in our computer. And the way we do that is to create a mimic of an antibody, which is like a beta hairpin, shown up here to the left. Beta hairpin, which has on the blue residue a structural site of the beta hairpin. On the red side, which extends out like millipede feet, we have the recognition residues. By using this template, which maintains its structure, which is a very important feature, it maintains its structure, allowing us to design the interaction of the millipede feet with the protein. This is now new because if we had an antibody, the antibody would not be directed towards a particular site of the protein. It would find the site where the antigen is, and that's where it would recognize. We can actually design our molecules to recognize any part of the protein surface, and that's what we have done here around interleukin 6. We have made two molecules, one which is attached to the bead, and one which is in solution with a fluorophore on it. This is just one design of two compounds. We have not designed a whole lot and tried them out. This is one design of two compounds. And we mix these and we see nothing. If we mix the two red and blue molecules, we see nothing. And then when we add just a tiny amount, 20 nanomolar of interleukin 6, we see it recruit to the bead and extract the fluorophore from the solution. So it works with two designs in a single go here. Can we use this for anything practical? This here is a plaque in the human brain with Alzheimer. And this plaque is characterized by fibrils made from the beta 1 to 42 and beta 1 to 40 peptides. And these were isolated by Greener, and they were used for making electron microscopy of the fibrils. So here is an electron microscope structure of the fibril that is actually isolated from the human brain. If we could now prohibit this fibrillation, maybe we could actually have some sort of cure for Alzheimer. So we were looking at how to cut this open into looking at the growth surface of the fibrils. So they grow like that from both sides. And here's one of the growth surfaces, and we design our molecule to fit exactly into that growth surface with all the appropriate interaction of charges and hydrogen bonds and so on. It worked quite well. Initially, we designed two molecules, just two beta hairpins of L amino acids, and you see on the upper curve, you see the fibrillation curve. We insert the fluorophore that is in the left corner there. That is inserted into the fibrils when they are formed and give a fluorescent signal by orientation. So the fibrillation curve shown in the upper slide, and then on the lower slide, the lower curve, you can see what happens if we add the peptides. There's a little bit fibrillation to start with, and then it completely wears off. We can also actually interrupt the fibrillation that's already started by adding our peptides at a later stage. But we are not quite happy. We didn't want this initial fibrillation and so on. And also we wanted more solubility of our peptides. So Yuan Zhang, he used glucosaminic acid, which has the same structure as D-threonine, and he inserted these into the beta bodies. So first he made a synthesis of the building block. Took quite a while to figure that out, but it succeeded. And now we have a building block that can be used in peptide assembly. So we assembled a number of peptides designed to bind to the two growth surfaces of the Alzheimer fibril. The question is, would that work? These are the structures of the molecules, and if you are a peptide chemist or a biologist, you will not really recognize those because they are mainly D amino acids, peptides, and then you can see the GAs is where we have the glucosaminic acids. Did it work? Yes, it worked fantastically. So on the top, you see the fibrillation curve without anything from A beta 1 to 42. And at the bottom, you have compound 3 and compound 5 mixed together. and you can see how well that is completely suppressing the fibrillation. So that works well, and it also works for 1 to 40, where we also have complete suppression of the fibrillation process. So what we think is happening here is that the water layer actually is captured by the compound. These antennae sticking out, they bind in a hydrogen bonding network to the water, and the water becomes part of the molecule that is interacting with the fibril, and that is why it works so well and also helps for the solubility of the fibrils. So we think we have these fragments formed, and we hope to be able to demonstrate that you can also get rid of these fragments in your deep sleep, just like you get rid of fuel that you have used during the day in the brain. Get rid of that during the night by squeezing the brain liquids out. Maybe this can follow that disposal. So we also worked with trying to actually cleave the Alzheimer peptide, because one thing is to hinder fibrillation, but if we could have a catalytic process that could just cleave it in the middle where it starts to fibrillate, maybe we can completely avoid this problem. And if we have selectivity enough, maybe even in a non-toxic fashion. So Martin Wolfram, he synthesized peptides which have carbenes in the center. So we can actually have a carbene precursor that we are inserting during synthesis. We deprotonate that, form a carbene that can then interact with a noble metal like palladium here, or even any other transition metal that binds to carbenes. And then we use that to cleave the substrate. This on the top is a FRET substrate, a fluorescence quench substrate. So when we cleave that, we see fluorescence. And it worked fantastically. So both with the carbenes and also with this bipyridyl residue, it worked amazingly. And then Martin thought maybe we can halve the amount of catalyst. So we did that, and it still worked perfectly. Then he took it to 1/5, and it still worked fantastically. And then he took it out completely, and it still worked amazingly. So what is going on? You know, it can't be the catalyst because we removed the catalyst. And here is another moment of serendipity where you really have to be observant and say, this could be something very important. So it works even without the organozyme, and we try to synthesize all the fragments that are produced in this hydrolysis. We produce them synthetically like this, and then we investigated the entire process. So this is the Alzheimer peptides, and these are the cleavage sites. Centrally in the nucleation site of fibrillation, we have this autocatalytic cleavage. And we can see it here in the HPLC stack on the left side. You can see a red starting trace. Then after a couple of weeks, actually 11 days, we start seeing second compounds coming up, then a third compound, then a fourth compound. So something is happening with time that gives us a proteolytically active aggregate. We can isolate all the fragments. We can also take a little bit of the most active one around F2, F1, the most active one, just a microliter of that, and transfer it into another Alzheimer peptide, and then we have the process starting there. So there's a real autocatalytic process going on here, where an enzyme-like moiety is formed that cleaves itself, this is the source of the peptide. And you can see there's also a delay in this process, so something has to form that is active. We also could take a beta 1 to 40, and when we didn't add anything, within 2 weeks, we saw nothing. Within 2 weeks, we added a little bit of the one from the HPLC traces, just 1 microliter. You can see complete degradation in 12 days here. So we thought maybe this is a real autocatalytic process. So we took a beta 1 to 42 and left it on the shelf. We looked at it once a week. Nothing happened. After 3 months, nothing happened. After 3.5 months, boom, everything is hydrolyzed. Fantastic, because This means that we have a delay process with a proteolytic activity. We also found that there's a process for fibrillation here. First, we form the donuts. They form small sticks. The sticks make a train, as you see in the lower picture, and this train then mature, as in the lower right picture, into a real fibril. So this is like the process of the fibrillation. Leshinska and her colleagues, they made some discoveries in 2015 of soluble NCAM peptides in the Alzheimer brain. So Alzheimer is surrounded by neurons that don't behave well. They are actually the adhesion molecules that keeps the neurons together and makes them functional. They are cleaved off and the neurons die. So this is probably one of the causes for the toxicity of the Alzheimer. Because if the neurons can't combine, they cannot survive, and we have neuronal death. And here you can see their experiments that shows a very large increase in soluble NCAM molecules, not capable of making adherence between the cells. In fact, they're actually inhibitory for the interaction, because now we have a soluble fraction that can interact with the normally adhesion molecule. That's really bad, and you can see the ratio is up to 10 of soluble to cell-bound NCAM. The molecule looks like this. It's a huge molecule, and we believe that this overlay here of Alzheimer A-beta and soluble NCAM shows us probably one reason of the toxicity in the Alzheimer case. So understanding this in detail is very important, and we are now trying to make various lengths of substrate and expressions to figure out whether our active Alzheimer protease can actually work on the NCAM to cleave those off. So we have here an animation of the proteolytic aggregate that comes in, finds its cleavage site, and cleave off the NCAM molecule from the neurons, and that's of course very unhealthy. So we have a way that the fibrils are formed, and we have the proteolytic activity, and both of those can be addressed now. The only thing that we really need now is to get into the neuronal cell, into the central nervous system. But before we do that, here is a picture from a nice holiday, very warmly recommended holiday in Stockholm. You get there, and then you are first you have a day at the museum to know what is going on. Then you have one of the most humble days of your life, where you have to present for 10 million people. That's what you see here. Initially, you're very nervous, but you overcome it, and at the end, you are very relieved. There's a picture of me and my friends at the stage over there. So we need to get into the cell, and here is a problem, because most of the cell-penetrating peptides, they rely on positive charge that interact with negative charge in the cell surface membrane. And most of them are quite toxic. So we would like to develop a molecule that is non-toxic and can do the same kind of job as the large cell-penetrating peptides with up to 10 arginines in the positive charge region. Because if we can do so, maybe we can use them for transporting cargo across this concrete layer of cell membrane. So Yuan Zhang developed this synthesis of 4 building blocks that can be used to make a library of peptides. These are prolines that sits in the turn region of the design peptides that we have made. We have made two types of cycles and some linear peptides, 16 peptides in all, as shown here. And we would like to see if any of these would be able to transport things into the cells. And in fact, a lot of them were able to do that at very high concentration. But only one single one stood out with low toxicity and very high activity at very low concentration. As you can see in this slide, the second to last line there, one peptide out of these 16 peptides that I showed here, only one peptide, 15 shown there, was actually active in transporting into the cell. And if we look in more detail on this, we have also compared it with the TAT peptide at the bottom. TAT peptide is a natural cell-penetrating peptide originating from HIV virus, and that is not nearly as active as our compound is. And what we are importing here is just a fluorophore, a small fluorophore. So we thought now, what can we do with this? First of all, here's the activity profile, and we can see that the amines on the protein is very important. If you look at the building block structure, rather than an oxygen, the active substitution there should be a naphthyl unit, not a aliphatic unit, and so on. So we can synthesize these compounds very well. This is the crude products of these compounds with a total dye on it, and this is a peptide that was successful. This is a TAT peptide, again, very successful synthesis. And we also then investigated how is this import actually happening. So it's a temperature-dependent process. As you can see, it increases, and it's also an energy-dependent process, because if we inhibit ATP synthesis, we get less import. We can also see the increase in import with time. Goes up to 12 hours increasing, and then it drops off. And finally, we can see the concentration profile, and it works down to between 0.1 and 0.3 millimolar, which is like 100 to 300 nanomolar. We still get enough material in than is biological interest of biological interest. And you can see the increase in fluorescence with the concentration. So here is the profiling with different import inhibitors. It could be passive import, but it's not. It's dependent on the dynamine type of endocytosis. So there's a number of different inhibitors that we can add, and the dynamine one was the one that gave you an effect. So it's dynamine-dependent endocytosis, and it works the same way with all these cell lines. So it's cell line independent import. There's one that's a little bit less, but generally it's more or less the same for all cells. So we made this with a click handle on it, this peptide, and we took hexahistidine GFP, and this hexahistidine actually allows us to do very selective N-terminal modification using an aceto-PEG NSH ester. So we can attach the aceto group at the end of the N-terminal of the GFP molecule, and then we can couple that with the cell-penetrating peptide and isolate it. And here's what happens if we just take GFP, nothing goes in at all. If we just take GFP and mix that up with our peptide, nothing goes in at all. If we then attach the peptide to the GFP molecule, you can see how much GFP actually goes into the cell, into small endocytotic compartments, capable of fusing again with the membrane on the other side, which is just what we want for blood-brain barrier penetration. So we can make these cell-penetrating peptides that increase the amount in the cells. They interact like that with the lipid bilayer, and here is just shown on the bottom the interaction of the arginines with the phosphate groups of the lipid bilayer and the deep burial of the hydrophobic part of the molecule. So we get this concentration of these molecules on the surface of a membrane, endocytosis is happening and it gets into the cell. We're back in Stockholm. This is the day where you have the ceremonial the ceremony of the Nobel Prize, and the king come forward with the Nobel Prize, and you get the Nobel Prize. It says thank you to everybody, and then you start with your Nobel Prize in your hands. You go for the seat, and then somebody comes along and takes the Nobel Prize away from you. You think, what? Did I say something wrong to the King of Sweden? But in fact, that's not the case. The problem is that many of us did our discoveries like 30, 40 years ago and have been actually victim to Alzheimer in the meantime. So a lot of the Nobel laureates forgot their Nobel Prizes in the ceremonial hall, and now you only get it on the last day, and then it's your family responsibility to get it back home. So the last that I will talk about here is a protein function. And this is a protein, papain, which has a huge hydrophobic core and a very small area of activity up in the cleft on the top. So this hydrophobic core is very, very important in protein function. And it's actually conserved between different protein classes because it's very difficult to make. Nature has developed these over millions of years, and they are actually reused. So the surface can change as you like it, but the core is often maintained. That is because we have secondary structure in the proteins. The protein are tactic molecules. They are all L-amino acids, projecting one conformation from one residue to the next residue into a helix, into a sheet, into other sorts of conformations. And these have to be compacted into a hydrophobic core that leads to the folding, that leads to the functional protein. So if we can do away with this tacticity, which is a consequence of the economy of protein expression, if we can do away with that, we can make much smaller molecules maybe that can actually function and have functions like a protease activity. Here's a small molecule of only 25 amino acids with a perfect fold, hydrophobic core, and a hydrophilic surface, soluble. So this is what we are looking at, and here is some proteolytic enzymes that we have synthesized. I'll focus on SP1 today, the most active one we have made. SP1 is a serine protease, SP is serine protease, and it has a fold that is very stable in the computer even without any kind of modification. It's made of L and D amino acids, and it can be further stabilized by bridges. Here's a disulfide bond bridge and a click bridge in the molecule that stabilize the structure, leading to a very stable conformation where the distances are maintained between the active site residues. And this can be synthesized again in 96 reactions. We get this molecule, and you can see the purity here of the crude product allowed by our very nice synthesis strategy. So we tried that with a library of compounds, 3.2 million substrates, and if we cleave this, they will be fluorescent because while the nitrotyrosine here is present, there's a quenching effect. It won't shine when we shine light up on it, but as soon as the nitrotyrosine leaves, the beads that we are making this on, they will shine light. And we can see that very clearly here, where we see the activity of subtilisin, one of the most active proteases out there. It's used in our washing powder, really, really powerful. And you can see after 30 minutes, we start seeing small rings on the resins, and eventually these becomes fully hydrolyzed within 24 hours. And there's still specificity after 24 hours. We also see some dark beads. So this protease seeks out the active ones and cleaves them. What does our protease do, which is a completely synthetic new protease? Well, after 3 hours, we start seeing fluorescent beads. 19 hours, 24 hours, 7 days. But my PhD student, Mads, did not really believe the results, so he just left it for a while to see if it really works. And this is after 3 months, and you can see there's still selectivity after 3 months, and it works on most beads. So we have a protease which can cleave substrates. We are in the process of analyzing what it actually cleaves and how. And this protease has 2 bridges, has 3 active site residues, a hydrophobic core, and all the hydrophilic residues that makes it soluble at milligram concentrations in per milliliter in aqueous solution. So we are back in Stockholm, and this is now the last day of the ceremony, and you have the ceremonial dinner. My wife, who is sitting down here, a very active person, she wrote to the art school in Stockholm and said, well, I saw a dress on the first day on a mannequin in the museum. I would like to have that for the ceremonial dinner. And I said, yes, of course. And they worked for 24 hours a day, and they made this beautiful dress for her. As you can see, it's really artist because it's 6-membered rings on the dress, not 5-membered rings, right? But when you dress your wife, or when she dresses up like that, there's a real danger. And here the danger is called Prince Philip of Sweden. So I was guided to the other side, and Prince Philip took my wife to sit between him and the other Crown Prince of Sweden. I was sitting down by the doorway. And then next day, I got revenge. This is a hotspot at an event at the castle. And this, of course, is the coming Queen of Sweden. So that's why I look so goofy on the picture. Thank you very much for your attention and for being here. I have to thank the people behind this. So first of all, my collaborations around the world, particularly in Denmark, but around the world, in Scotland, in Australia, and many other places. And also the people from the Carlsberg Laboratory. There's quite a lot of them. A particular thanks to Christian Tornø for developing with me the click chemistry, and also to all the other people who have been involved in the development of click chemistry over the years. Same thing at the University of Copenhagen. Quite a lot of people, particular thanks to Martin Wolfram for the Alzheimer's story, and to Hong Xiaohu, Susanne Soffelin, and Jan Sang, to Sarah, Mads, and Niklas, and many other people in the lab for the proteolytic activity work. And finally, to my family, to scientific discussions with my very skilled wife in chemistry. This is, of course, very productive when you have this option at home to discuss chemistry when you have problems in the laboratory. So thanks for that.
Thank you, Professor Meldal, for the informative and inspiring presentation. And I love the dress, by the way. We kindly request that you remain on stage. And we would also like to invite Dr. Hassan Ba'aqil to present a token of appreciation to Professor Meldal. I mean, we don't always have Professor Meldal on campus. Thank you, Professor Meldal.
Thank you very much for this. It says, in application presented to you in recognition at your contribution as keynote speaker. Thank you.
And now, ladies and gentlemen, building on our theme, Our next keynote speaker is from Stanford University. He's a King Faisal Prize laureate and a scientist whose pioneering work in laser-induced fluorescence has transformed the way we understand chemical reactions on the molecular level. Please join me in warmly welcoming Professor Richard Zari to the stage.
Pleasure to be here. I need a little bit of help to know where is the device. Aha, I see something here. Let's begin. If I push this green thing, what will happen? Nothing. Okay? I'm sorry, I have no instructions how to make this run. Can someone help me? That didn't work. This? Nothing? Sorry, I have no idea. Where is their device? Is that something? This goes forward? Good. I'll have to look at this since I don't have something in front of me, but here it is. Can you hear me? No. So I don't have a microphone either? Microphone? I'm stuck. Stuck back here. Okay, let's try. We'll stay here then. I want to speak to you very much about interfacial curvature, not surface area or volume, that controls water droplet reactivity. I'm going to begin with some facts about water. Water, we know, is benign. We swim in it, okay? We drink it. Life needs it, etc. It's good for dissolving polar things, but unless you drop sodium or something into it, nothing much happens with water, you think. What do we know? Bulk water is neutral and contains equal but very small amounts of two ions, H plus and OH minus, the hydroxide ion and the hydronium ion, OH minus and H plus. Water droplets turn out to be highly reactive, facilitating the formation of radicals and promoting redox chemistry. I've been working with Professor Bashir here for a number of years, and we've made some amazing discoveries, we think, about how you can use water droplets to take the nitrogen in the air and turn it into ammonia at room temperature, okay? And to add carbon dioxide and make urea. How you can actually turn methane into methanol and help remove methane, we hope, from the air. All types of things are being done with water droplets that are quite exciting, I think. Water droplets are charged. Larger ones are positively charged. Smaller ones are negatively charged. Water itself is not charged, neutral, but in forming droplets, they get charged. You even get sparks that can fly between the charged particles, but that's another story. I'm not talking about that now. I want to give you a sense of how the field of microdroplet chemistry, really the chemistry of interfaces between hydrophobic and hydrophilic media, have grown. Look at this. This is a plot as I see years, and I see the publications involving microdroplets and reactivity. And it's taking off, much like KFUPM, going way up very rapidly. I think it's impressive. You can see the countries that are involved, and at the moment, the United States is slightly leading, but this may change. Okay? We'll go on. The question might be, well, what makes all this happen? And you might start by asking a beginning student in chemistry, here's a 1 liter beaker of water. It's pure water. What's inside it? And we see it. And the beginning chemistry student says, I know the answer. After all, the mass of water is 16 for oxygen and 2 hydrogens, 18. And this weighs 1,000 grams. That's 1 liter. It's 1 gram per milliliter, right? So the answer is it's 55 moles, and there's an Avogadro's number in a mole. So there's a huge number of bent HOH molecules. And you say, okay, fine, that's the answer. What else is there? And the person looks at you a little bewildered and says, are you talking about isotopes? And I say, no, I understand isotopes. I'm saying what else is in water. And actually, the person says, I learned there's 10 to the minus 7 moles of H plus and 10 to the minus 7 moles of OH minus. And that's why everyone who begins chemistry starts with the idea that the negative logarithm to the base 10 of the H plus concentration is the pH, and pH of water is 7. So far you smile. You say, well, have you ever thought about what do you think is the pH of a water droplet in air at its surface? And the person looks at you, and you're a professor of chemistry, so probably the answer is not 7, but what is the answer? And this is not anything that's taught much. So we're going to actually look into this in more detail. I want to show you, in bulk water, H plus and OH minus are completely surrounded by other water molecules. They're solvated in 3 dimensions. And consequently, the electron does not jump from the OH minus to the H plus. You don't form the hydroxyl radical, OH dot, or the H dot, which is the hydrogen atom. Electron transfer is endothermic, and you can calculate it, and I'm showing it to you. It's really quite endothermic, doesn't happen. If it happened, then water would be bubbling all the time, H2 out. It doesn't happen at all, right? We know that. Now, here's the thrilling thing to me. Liquid water at the air-water interface, when you calculate it, this transfer is exothermic. It really happens thermodynamically. Why? Well, you no longer have 3 dimensions. You can't solvate in 3 dimensions. Indeed, in the gas phase, if you brought a negative ion and a positive ion close to each other, you get an electron transfer. What else? There is a huge electric field at the interface. People who study biology or biochemistry know this all the time about membranes, but don't think about it as much about a water droplet in the air, but it's still also true. And how do we know it's true? Here's work by a person who was a postdoc in my laboratory, Yu Xia, who's just gone back to China at Jianghan University, be an assistant professor, and he's using a spin trap to capture radicals. And what does he see? He's able to capture the H radical, the hydrogen atom, and the OH radical, the hydroxyl. So we really know it's true, no question. We'll go on. At near the surface of the water, microdroplet autoionization is greatly enhanced. At the microdroplet surface, the OH minus loses an electron to form the hydroxyl radical. The hydroxyl radicals in solution then find each other, and they recombine. When you make them together, you get HOOH. What's that? H2O2. What do we call that? Hydrogen peroxide. So we see that hydrogen peroxide is being formed in this way. There are people at other places, like KAUST, who don't believe what I'm saying, but I believe this is what really happens very much. There are other ways to also make hydrogen peroxide, but clearly it has hydrogen peroxide. I remember being so excited when our lab first saw this. J.Q. Lee in my laboratory, we submitted this paper to Nature, and it was sent out for review, which I was pleased about. The reviews came in mixed from this is fantastic to I don't believe it variety. And then finally the editor, well, I'll leave nameless for the moment, said to me, if this were true, people have been studying aerosols for years, they would have seen it already. Well, it is true, but it wasn't reported, and it missed it because it turns out you need little droplets to really make this happen. How do I know that? Here is a material that was made at UC Berkeley by these people, and this thing called PF1. It has an IUPAC name that's hopeless to say. I won't. Okay? And hydrogen peroxide clips that boron-carbon bond, and you get, shown on the right, what you might recognize as fluorescein, something that fluoresces when you shine UV light, blue light on it, okay? And so I'm showing you, here is PF1 in bulk water. The top is fluorescence, the bottom is bright field, so you can just see the water. Nothing's happening. Here is an air-water layer, flat air-water layer. You see any fluorescence? I don't. Okay, now look at this. Here are droplets. And moreover, the little droplets are even brighter. How do I know that? Because we're able to actually make a study. Let's pay attention to this study now. What do we see? Don't know how, is this a pointer? No, I don't have a way of manipulating a pointer to show you. Look, you have 3 droplets. The first one, A, 160 microns. Only those maybe in the front row can see a little bit of green, okay? B is 50 microns. Now I'm starting to see the fluorescent green. And C, 60 microns, look at it light up. And you're seeing on the right this graph of microdroplet diameter. So here's the first hint that really smaller is better in this case. Really much more active. You with me so far? I hope so. Okay. Now, but why? What's going on? We're going to go on to study this. And here I'm showing you a measurement that was done with Professor Wei Min and his student who's now back in Beijing, Shang. Anyways, this is work we did on strong electric field observed at the interface of aqueous microdroplets by the Stark effect, how the spectrum shifts its peak as a function of applying an electric field to it. That's a Stark effect. And what do we calculate from this? We calculate from this something like 10 to the 7 volts per meter. Now, to me, that's a huge field. It's nothing compared to what the electron feels from the proton and the hydrogen atom, but it's still a huge field, much larger than you'd get in the lab without getting lightning to happen, okay? And you get this type of thing happening here. We'll go on. Here's some work done in my lab by Kyungmin Lee, who's back in Korea, and Masoud Mirgardi, who's back at the University of Isfahan. And they're looking at early evidence that curvature of the droplet is important. And they're showing you various size. See the radius? Same idea. See how it lights up again? You get the smaller. And they've actually made a study of this. And they actually find that if you plot it as against the normalized area against 1 over r, you can see in the middle there, it's nearly a straight line. It's depending, when you normalize for area, it's depending on 1 over r. What's going on, okay? Obviously, some form of curvature. Let's see if we can understand this better in the short time we have. Here's more work done by other people, researchers in my lab. This is an experimental setup, droplet on demand mass spectrometer. We're going to use a piezoelectric device to fire this. And now, I don't know how to make this play, but those in the back can make it happen, right? So please show this video. Would you please make the video happen? This is why I wanted to use my computer. Okay? Let's go back and show the video. Go forward. Here we go. Now play the video. You have to click on it to play the video. Well, we have a failure. If you could actually see the video, you would see, here we go. You can see the droplets, and then we can control them one at a time. Okay, and we know their size. And we're going to be studying one droplet at a time. And I thought this is important that you see this, and so you can believe what we're studying and understand how this is going on. And let's go to who does this work. And this is, again, Yu Sha, with other people like Bo Lei Chen and Xinxing Chang, okay, from these places. Mostly this is work done in a collaboration with people in China. And let's look at the mass peak at M over Z equal 36. It's called the water diameter cation. It looks like H2O twice with a plus sign. Actually, I think it's primarily OH coupled to H3O plus. And that's what I think structurally is going on. Anyways, whatever it is, we're going to use this intensity, which we denote as I36, as a measure of how reactive is the water droplet. Agreed? Okay? And we're going to look at that reactivity. let's see what we see. Here is the droplet surface area, and here is the intensity of I-36. And we're seeing if it depended just on surface area, it ought to follow that red line, that dashed red line. Doesn't do that. It's bending over. Instead, let's take it and normalize it by the surface area and look at it 1 over the droplet radius. Nearly a straight line. Not quite, but nearly a straight line. It's really depending on curvature that I'm telling you about. And finally, I now want to get to where this comes from. This part of the talk is technical. Anybody who wants a copy of these slides, please just email me at my email address, which is my last name, Zare, at stanford.edu, and I'll give you a copy of this so you don't have to take notes. But let's go through this. We begin by considering a sphere of uniformly distributed dipoles having an infinite radius. That is a flat sheet having no curvature. All the dipoles are going to be aligned. Okay? Here we are. We start by considering an infinite plane of positive charges with charge, this sigma, okay? Electric field is produced by this plane. Because the plane is infinite and uniformly charged, the field must point perpendicular to the plane, no side lace, okay? Field must have the same magnitude on both sides of the plane. And using a pillbox, a short cylinder of top and bottom surface area A that straddles the plane, and applying Gauss's law, now we've wandered off into physics, I think, right? At least into understanding electricity and magnetism. The total electric flux through the pillbox equals the total charge enclosed by the pillbox, namely sigma A divided by the permittivity. E equals this. And the magnitude of the electric field is constant above and below the plane. And electric field of a plane of dipole moments, each pointing in the same direction, perpendicular to the plane. And I'm showing you, consider it with plus sigma and minus sigma. When you add them together, what do you find? There is no electric field. If you have a capacitor, there's no electric field above and below a capacitor. Big electric field in between, but none, okay? Very important idea. Now, let's take this capacitor and bend it. Let's bend it towards making a sphere. And of course, surface tension does that. And so we're going to consider a solution that forms a spherical droplet. There are two kinds of ions, positive and negative, as shown here. We assume the solution is overall neutral. That means the same number. We'll call the concentration C0. We're going to put these together. In the region where the electrostatic potential is psi of r, the ion concentrations change. And from statistical mechanics, they follow a Boltzmann distribution, as shown in this slide, like so. Okay? Where r is the radial distance and kb is the Boltzmann constant and T is the absolute temperature. Okay? And the net charge density is then given by putting the sum together. You'll recall maybe what a hyperbolic sine is. It looks like this. And so we obtain that rho of r is this quantity is shown in the middle here. And the consequences are this sort. This is the type of thing you'll get when you work this out. Very simple model. The nonlinear nature of the hyperbolic sine function captures how charge builds up near the surface, not linearly, but more sharply as the potential increases. And then using a Taylor series expansion for the hyperbolic sine, we have something like this. And if x is much, much less than 1, which is normally the case, you just need the first leading term. And that's how you get that rho of r looks like what's shown at the bottom here. And this is known as the Debye-Huckel approximation, worked out in 1923. And it's the basis of people understanding electric double layers, electrostatics, very much. What we're going to do next is define the Debye length, as shown here. And the dielectric constant of bulk water is about 78.5, but at the surface it's thought to be much smaller. We'll work all this out. We're now taking the radial distribution of electrostatic potential as governed by the Poisson equation. We do the differentiation. We find what psi of r is, as shown here, okay, where a is the undetermined constant. And we're now going to take its derivative of the potential. When we do that, negative derivative of the potential, we get this thing. There's a kappa over r. Remember, 1 over kappa is the bi length, and 1 plus 1 over r squared. So at the droplet surface, we actually work out what E of r is substituting back in A. It's 1 plus this 1 over kappa r. And what I'm trying to tell you is that you really have, when you bend this, a dependence of 1 over r, a constant term plus a dependence of 1 over r in this. And now, again, is this so? Yes. This really is a very simple model, and it helps to explain what we're seeing. And is this then the end of the story? I'm worried about my time. Make sure I'm okay. Coming close to the end. Okay. Is this the end of the story that I've just given you? Fine, about curvature. And you say, well, okay, what happens? No, it's not. Because more hydroxyl radicals are generated as the radius of the water droplet shrinks. There's actually going to be a competition between OH combining with itself. That'll be quadratic in the OH concentration. And OH reacting with something, okay, which will go on to make products. And the result of this competition is that the rate of production becomes optimal for a specific water droplet size. So I'm telling you, and I think this is quite interesting, that it doesn't just always get better the smaller you make it. It's actually, there's a maximum size that works. And I'm going to show you this. Here's an example. This is melatonin. We see what it is. And I'm giving you a mass spectrum, and I'm showing you that melatonin captures OH. There's melatonin with the OH plus. That's at 250. So let's look at the intensity at 250. And here we are plotting it. And if we plot it again versus droplet surface area, same behavior as what you saw with hydrogen peroxide. And now 1 over the droplet radius, almost a straight line. And if you now look at the product of what you're making with melatonin, this is the oxidation product as a function of the inverse droplet radius. What does it do? Shown way on the right, it reaches a maximum. Where's that maximum? Looks like around 0.15 or where? No, 0.10? Looks like it's about 10. That's 1 over the radius. That's 10 micron radius. Okay, is best. Now, let me show you that this is general. This is methyl viologen, or known as paraquat. It also, here's what it is. It also captures electrons. It accepts 1 electron to form the methyl viologen radical cation. And we'll look at it. Here it is. Here are the things that it's generating. Okay? We've studied this before. And the total product signal will be the sum of these three, the 171, the 185, and the 186, all these things that are generated. And let's now plot it. Again, droplet surface area, that's not the answer. Okay? 1 over the droplet radius looks like it's linear. But look at the product. The product reaches a maximum. Different maximums for different things. This one seems to reach a maximum around 0.2. So it's about a 5 micron radius, 10 micron diameter type droplet that we see here. Fantastic. Now, in a short amount of time, if there is any left, 3 minutes maybe, something like that, I want to show you some more results. This is a collaboration with Professor Di Wei in Beijing, and I want to talk to you about making bleach. Because I want you to see that this is actually, it sounds very hypothetical, that there's actually some practical possible consequences. Okay, let's go on. How is bleach made? Today, one makes bleach by taking salt water and doing electrolysis. And you get, what do you get? You get chlorine gas and you get caustic soda, and then later on you cart them off and you mix them, and you end up with a sodium hypochlorite, and that's the active bleaching compound, which is sold as a liquid bleach. Bleach is a great disinfectant. Okay, ask my daughter Rachel in terms of medical uses. It's really important. Okay, great. What do? We do this in droplets. Droplets in which we expose them to a hydrophobic medium. What hydrophobic medium? Actually, fluorinated ethylene propylene. And here's the type of chemistry I'm showing you. OH dot plus Cl minus goes to form dot OH Cl minus. Where's the Cl minus coming from? Salt water. I told you we're working with salt water. Okay? And then you can read the rest of it, and you go on and you form HOCl and OCl minus, and that's your hypochloric acid that you get from this. So it really is so, and I'm really, again, trying to show you the difference. We have a green chemistry for doing this with no applied electricity. All the electricity is coming from this interface, from the droplets. It's done at room temperature. It's a green chemistry with seawater, okay? And I wanted you to see something of the thrill of what's possible with this type of interfacial chemistry. And I think there's a huge future ahead that's many things to play. And with Professor Bashir, I've been very much inspired by all the things that are possible this way. And I think I end up by now just showing you how the size of the hydration shell varies with the nature of the alkali atom. I think I'm running out of time, so I'm going to go through this very quickly. It really depends on whether you use sodium chloride or potassium chloride or lithium chloride. And you can go through an explanation why this is so. And I'm showing you it really matters what you put into the double layer, how you affect the electric field, and how it then changes the production of the OH radical, which again leads on to react with the chlorine minus to make bleach, okay, through this process. And so reduced cation hydration sizes enhance both the interfacial triboelectric field effects governing ROS kinetics and the local anion concentration of the reaction result, resulting in higher active chlorine yields. Why haven't you read about this? Because it's under review, okay? But I'm giving you the type of results that you're seeing. And I thank you very much for coming and listening to this and learning about how curvature really matters in water droplet chemistry. Thank you.
Thank you, Professor. We would kindly request you remain on stage. And once again, I would kindly ask Dr. Baqil to come on stage to capture this moment with Professor Zaria. Thank you, Professor. Continuing our keynote sessions, we are honored to welcome a leading figure in nanotechnology, the discoverer of carbon nanotubes, and King Faisal Prize laureate. Please join me in giving a warm welcome to Professor Lijima.
Can you hear me? Okay. How do we change the slide? Let me see. No. How do you? This. Oh, okay. Okay. All right. So, good morning. My name is Miyajima. I'd like to thank the organizer to invite me to this wonderful meeting, exciting meeting. Let me see. I started this one. Okay, so far we have heard the lectures, but in my talk there is no equation. So sit back and relax and just watching the picture. Okay. Here now you are looking at the atoms of carbon under the electron microscope, okay? So if you look at the, no, not this one. Let me see. No. Okay. If you look at the right-hand side up, and you see some dark dots. Okay, inside the carbon nanotube, and you see the fluorine molecules inside the carbon nanotube, and this is the beginning of the shooting, and you see the dark dots on the molecule, and if you look at this one. And on right-hand side, there is no change. But the left-hand side, those molecules are growing. And onto that, we have the one metal atoms. It's going to be the catalyst. So going back to the original, the starting. So now you are looking at the reaction, chemical reaction under the microscope at atomic resolution. Underneath, we have this is graphene, tip of graphene, and you see the string of dark dots. Those carbon atoms chain. That's a single chain, okay? And now you see the double chains, and it's a single chain and the break. This is the beginning. So we are really looking at the individual carbon atoms under the microscope and the reaction. And so this is the beginning of my talk, okay? And my title is High Resolution Transmission Electron Microscopy and Discovery of Carbon Nanotube. Because I'm not trained as a chemist. My background is physicist, okay? So no complicated equation here now. Right, so okay. So I have to start with this picture. This year, May, I came to the Riyadh to receive the King Faisal Prize. So I'm very proud of this prize. So I had a good time at Riyadh, but this city is my first visit. Anyway, so this is my first one. Then yes, because citation is discovery of carbon nanotube, right? Right. So I'd like to speak about the simply. Oops, here. No change. How do I do it? How can I do it? Let me see. That's why I want to use my own PC. Can you help me? Let me see. Oops. I can see the screen slide here, but not there. Okay, can hit this one? This one, okay. Okay, so perfect. This one, right, okay. Yes, I finished this one, discovery of carbon nanotube, and I like to speak about the, oops. No. Oh, yeah. So what's a carbon nanotube, and what is it for, and how did I find it? And last one is the modern electron microscopy of complex oxide. This is not about the carbon, but oxide. Okay. Here, she said, push this one. No. Why did I do it? No. It's going backward. This one? This one? Then, okay. All right. This one, right. Now I know how to do it. All right. All right. See, wait. No picture here. Continue. This one? Okay. Okay. So this is first slides for the discovery of carbon nanotube in 1991. This is a bit technical. And we had, I can see here, but no screen here.
Ladies and gentlemen, we just request a few minutes until we fix this technical issue. We appreciate your patience. Thank you.
Okay, I think that the picture seems to be fixed now, but I need the microphone, but I can use this. Oh, yes, coming, yeah. Okay, so continued. Right. So the, yes, content, I told you, what, right. Then the discovered carbon nanotube. This is my first report in Nature, 1991, so nearly 35 years ago. It's old story now. This electron diffraction pattern, when I had this paper, someone claimed, wait, I did it before you, but they showed just the micrograph, okay? So micrograph may be carbon nanotube, but the maybe something else, or amorphous carbon film or something. But what you need in scientifically, we need the electron diffraction pattern. So that's shown on right-hand side. This tells you this structure is really consisting of graphite structure. So this is essential. And the people didn't show this before. So graphic structure, then we have this kind of, and then next one, some theoretician told me this, since you discovered carbon nanotube, but your carbon nanotube with 2, 3, 4 the cylinders, so it's too big for the computer calculation. So theoretician like Marvin Cohen at Berkeley and Sumio, why don't you make the small carbon nanotube that fits the calculation? Then this is the picture, okay? But to do this, I spent 2.5 years to produce this one from the first one, because there is no recipe to make this kind of thin, small carbon nanotube. But so that's a science, okay? It's very challenging. But I accidentally, actually, I found this single carbon nanotube. Right, so yeah, again, I showed the electron diffraction pattern. These days, it's not so difficult to electron diffraction pattern, even 1 nanometer carbon nanotube, but this was 30 years ago. It's not easy, so I did work really on high-resolution microscopy, but I did. Okay, so then, yeah, this we can have this kind of high-resolution micrograph of individual single carbon nanotube. Then we can tell what's the atomic structure of carbon atoms network. So that's easy. Then you can find the chiral, the structures, or straight the carbon nanotube atomic structure from the electron micrograph. So this is the kind of technique I used in my experiment. All right, so next one is the attraction of CNT. I can give you 3 examples of the application. First of all, the contribution to the sort of basic science, physics, chemistry, and nanoscience, or even the medicine. So many people, the researchers working on this material these days, okay? So first one, the basic science contribution. And secondary, of course, the industry application, what is it for? Carbon nanotube is useful or not? But many people are still working on this material, display devices, energy batteries, fuel cell, and electronic devices. Yes, months ago, there was a good news to me. Terahertz transistor was developed in China, actually. So this is a big challenge. They are try to compete with the silicon technology because much faster. So terahertz transistor is really getting real now. So the structural material fiber film, I have one picture, okay? Medical diagnosis and then testing in medicine, there are others. So many applications on this material. Okay, so a month ago, I went to Rice University in Texas, Houston, and there was one demonstration. Okay, this is, this is carbon nanotube swing. Okay, carbon nanotube is mechanically tough material, stronger than the steel. So the professor, Pasquale at Rice University, they had some company or something, and they demonstrated this thing. So I tried this one. So it's really becoming real now. Okay, so this is the mechanical application of carbon nanotube. The next one is the yes. When it started carbon nanotube, it is very good electron emitters. Okay, so you can extract a huge current from tip of thin carbon nanotube. So this current is going to be used for generating X-ray now. Okay, so it used to be this is used for the display, but display application is disappeared. But this one is an X-ray. Okay. Here is cartoon. Here, the electron coming out from carbon nanotube. Then hits the metal and they produce X-ray. So one of the American Chinese professor they utilized this technique, and then this is for the X-ray the scanners. Yes, this is for the medical application or dentists. They can build the movable, the handy X-ray small machine. I think I met the Professor Liu here. He just started the job here, and he's one of the developer of carbon nanotube. So I immediately found this place is going to be sort of the very active place of carbon nanotube developing. Please do so. Please support him. Okay. Right, so then he said also this is the scanner at the airport. You have carried the big luggage and put them in the big box and then and check the something inside. So this is now commercialized, and then the Professor Liu told me the first one was now you can see at Hong Kong airport. Okay, so this X-ray scanner, because one advantage is we can have a very small X-ray resources. So it's not one X-ray source, but you can have many. Okay, so immediately you can 3D images using this carbon nanotube, and even a very small one. A good application. Okay. What else? Oh, this is the latest application. Without this, you cannot have a 2 nanometer transistor now. Okay, so Dutch ASML and IMEX, and they are developing the what we call the EUV CNT pellicle film. EUV is the ultraviolet. And light for you lithography. Okay, so in some process they need to protect let's say pictures using these very thin carbon films. Okay, so without this film you cannot make the 2 nanometer the transistor. So this is a very, very essential part of this the high-tech application. So I'm very happy with this kind of latest application. So this is just happening last year or 2 years ago. Right. Now the background to discover the carbon nanotube, why I did find this one. I need 1 hour to explain this, but I make it very short. Right, so I told you months ago I went to Rice University where we had the anniversary of discovery of fluorine C60. Richard Smalley and Harry Crocho and Carl, these guys discovered, found the fluorine molecules at Rice University. So they organized the celebration for this discovery. And then I was invited there. And I talked about the early days of nanocarbon research. Because unfortunately, all these big guys are now they passed away, unfortunately. But I may be one of the survivors, okay? And so that's why they invited me to write. Anyway, so and then where I talked about the old story, how they discovered the C60, and I was partly involved in this the discovery. Okay, structural instability. Before that, I show you one picture, but maybe it didn't work. I have to hit, but I don't know. Before the discovery of carbon nanotube, I did a lot of electron microscopy of nanostructure. This is one of them. This is gold, very small gold, nanocrystal. And if you look at them under the microscope, they are moving, okay? And those the frame pictures from video pictures, okay? It's not only moving, it's inside the atoms all the time they are rearranging so that you can see different arrangement of nanocrystal, cuboctahedron or icosahedron phase, and also twin phase. So they are changing all the time. So this is the interesting phenomena of nanomaterial under the electron microscope, under the electron beam. All right. So what was next? Yeah. Next one is if you have the carbon crucible and break it and they put them in the microscope, what you can see is the next one. So this is graphene, the structure, atomic structure, okay? So this is basically the graphite structures. And this was in 1970s, okay, nearly 50 years ago. In that time, the graphene, this kind of graphites are sort of standard material for the electron microscopist. If you can see this C spacing, 3 points, 4 angstrom separation, we can see clearly my microscope is okay. Otherwise, you have to work on to tune the microscope. All right. So this is very familiar structure. Then some years later, we end up with C60 or graphene. So there's 3 layers there. So I worked on this one. Then the next story is that during this time, really, I missed the Nobel Prize, okay? Because when the Smoley, the Kroto discovered carbon the fluorine C60 molecule, they show just the mass spectrum. So it's a big peak, C60 peak, and 70 peak. Nothing to do with the structure, because there no evidence, scientific evidence to show this suckable molecular structures. But in their first paper, this is a speculation. It's not the scientific, because could be something changed or something, you know. But the C60, but they are the smart part of these guys. And they had the suckable model. So this is just a speculation. There's no scientific support. However, one of my pictures is only supporting their postulated C60 molecule. So this is here. And I published these pictures 5 years before their discovery, okay, 1980. Already I published this one in English journal. Anyway, yeah, as you can see, at the center of this, what you call the onion structure of graphite, spherical structure. At the center, there are some spherical structure seen. So the Smoley Kroto like this picture because this is only evidence to support their postulation. So I have acquainted with him, and even they come to Tokyo to meet me because of this picture. So I was very proud of it. Anyway, so and let's say this is interesting. Pentagonal rings should be pentagonal rings. This is my paper I said, okay, and even I said. You can see red line. There must always be 12 pentagons. I said this one 5 years before their report. So I really, but I am not smart enough to have this soccer ball, okay, when I wrote these papers. But I said that in order to explain this spherical shape, we must have the 12 pentagons, okay? So this is the soccer ball, actually. So that's why I said I missed the Nobel Prize. And then, I told you, even they came to Tokyo to meet me, and these exchanging the letters, okay, they liked it, appreciate it very much of this high resolution micrograph of soccer ball. Anyway, so in that way, I printed with small and Kroto, and then this was 1970. There was a big event happened to science community. The C60 becomes a superconductor. So all the people are excited about this discovery. And then this is Boston MRS meeting. I was there. And then I met again the Smalley and Kroto. Kroto pursued me, why don't you do the microscopy of the fluorine, the structures? So then I back to Japan, and immediately I started to find the soccer ball structures, graphene structures. And then a few months later, I incidentally came across the carbon nanotube. I have pictures here. Right, Smalley and sorry, Kroto. Then they prepared the what we could use the arc discharge method. This is this. In this smoke, if you do the arc discharge of carbon electrode, then you produce the smokes. Inside smoke, you can have the fluorine. But those are seen in the smoke. But I somehow picked up this, used this carbon rod and the tip of this rod. You can see dark things. And I scratched off the surface of carbon debris after producing the C60. So where I discovered carbon nanotube on that. People are looking at this the smoke for the C60. All right, so that way I found carbon nanotube. Yes, this is another picture. Looking for the onion structures, and yes, there are a lot of the blobs structures there everywhere. But if you look at it carefully, there are very fine fibers also everywhere. So my interest immediately moved to this fine filament, not the carbon, the onion structures. That's how I come across with the nanotubes. Okay, and then by that time I have enough technique to characterize this nanostructure using the microscope, and then also electron diffraction technique and analysis. So immediately I know what happened to these fibers. So then I published this one in Nature. Okay, so I think that's finished with the carbon nanotube. Completely changed the subject. Since I'm an electron microscopist, I have been doing a lot of the microscopy on oxide. So I give you one example. This is very, very interesting. You can find. Okay, I moved to the Arizona State University from Japan. I spent some years there. And then this is my first high-resolution micrograph showing the atom in the crystal, okay? So this is ternary oxide, titanium niobium oxide, the complex oxide. So this is the world's first high-resolution micrograph showing the atomic images. So that's the beginning. And then the next one, yes, this is the only 2021. Okay, one of the authors, John, good enough is one of the authors, Nobel laureate, about the lithium battery, the material. So TiNV207. I have looked at the Ti2NV10O25. So the same structure. Okay. So these materials are useful now. Is going to be used for the the battery, lithium batteries now, right? But these people don't care about how the titanium, niobium, how they are located in the crystal. So ternary crystal, they call the solid solution. Okay, they don't know. They don't know. They don't care about where it's in the niobium or titanium. They don't care, but I care. Okay, now I started to do work after 50 years. 50 years, okay, half century later, because I know this crystal, the structure is very, very well. So then the first one, this is 50 years old picture, okay. So and then structure is, of course, actually people already proposed this structure. And then 2021, okay, 50 years later, I'm going to show you the latest image. So same the material, same unit cell, and you can see the left-hand side, the right-hand side, and then you can see more black dots. Big one is the metal. But metal, small one, is even you can see the oxygen in the crystal, okay? So still black and white. Where it's in niobium, where it's titanium, we cannot distinguish them. However, if you pay the maybe $3 million to buy the microscope, you can see it. Okay, I cannot afford it, so I borrowed the microscope. And then, yes, I told you it's the solid solution. Titanium, where it's niobium. Now, they are not the solid solution. They are nicely ordered. So next picture, after paying $3 million, you can get these images, okay? So this is not the electron the images, but X-ray images, okay? So what we call the STEM EDX images, okay? So now the titanium, niobium, even you can see this, the oxygen is a crystal. So titanium is blue, light blue, and the niobium the pink colored. So they are nicely ordered. It's not disordered. So with the modern electron microscope, you can do this kind of atomic resolution chemical analysis. This must be important for the lithium battery people, right? Right, this is, you can see the niobium atoms and also titanium and even oxygen. And there are some another interesting the problem, but not now. I skip this one. So from this, if you look at carefully, still you see a very faint blue point. That means where that point still we have some the titanium there. So because this is ternary oxides. So then in the table we can estimate the occupancy at these positions. So this is not completely ordered, but there are some disordered region areas. Okay, so this kind of information you can have from the micrograph now. All right, I think with this I finish my talk. Right, summary. Right. Let's see. Yeah. In the first part, I talked about the carbon nanotube, and then the last part, shortly, I introduced modern electron microscopy of complex oxide. But I had another subject. This is another my interest. The photothermal acoustic phenomena of CNT. This is a different subject. Maybe the next occasion I speak about this interesting subject. Okay, with this I finish my talk. Thank you very much for your attention.
Thank you, Professor. I kindly request you remain on stage, and I would like to invite Dr. Hassan Ba'aqil as well. Thank you, Professor. And now we'll take a short break for lunch and prayer. Following the break, we will resume with exciting series of panel discussions. So enjoy your break. Thank you.
Check, check, check 1 2. Hello, hello.
والله الحمد لله كل شيء تمام. مع الار ان دي؟ انا مع الار ان دي. الله الله. ايه ايه هو قاعد يتكلم.
Okay, Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. Alhamdulillah wa salatu wa salamu ala Rasulillah. Welcome everyone. I know the session after lunch is always difficult to get people back, but really appreciate coming here. Thank you for the organizers for allowing us to have this very important panel session titled Translating Innovation in Chemistry from Lab to Market. My name is Ahmed Al-Fadil. I'm the Executive Director for Innovation and Technology Commercialization at Dhahran Techno Valley. If you may know, Dhahran Techno Valley is an arm of King Fahd University of Petroleum and Minerals. We are mainly the operator of the Dhahran Techno Valley Science Park. We are an innovation hub, a catalyst. We're really looking into translating deep tech innovation from lab scale to the market. This topic is very close to my heart. It's close to the function that we are doing, and also the kind of activities and initiatives we are trying to bring to the Valley. We're very thrilled to have distinguished speakers, experts from the industry, the SME field, coming us here and also helping us to share some perspective, their thoughts and their experience on the journey for translating innovation in chemistry from the lab to the market. We have with us, of course, we'll get the opportunity to introduce them further, but we have Dr. Mohammed Al-Amer, Chief Technologist of Fuels and Chemicals at Aramco. We are also thrilled to have with us Mr. Mohammed Al-Ibrahim, General Manager for Research and Innovation, and Mr. Michael Muller, Chief Vision Officer with Prime Vision, placed in Dhahran Techno Valley. Welcome all. I just want to start the discussion, and maybe you can introduce yourself before we get to the question. But with Dr. Mohammed, as a technology expert, when it comes to scaling and adoption of technology, so beyond like the simple volume, the lab scale development, from an industrial point of view, to translate innovation, like from the ideation to the development to the validation and planning the technology development to go all the way to be deployed or potentially commercialized. How does that journey look like from the industrial R&D point of view, and how does it compare to what happens in academia and research institutions?
Okay, assalamu alaikum. Thank you so much to Dr. Ahmed. Okay. Thank you so much, Dr. Ahmed, for the kind invitation, and thanks for the organizers. It's always a pleasure to be back at King Fahd University of Petroleum and Minerals. I'm the Chief Technologist and Manager of Fuels and Chemicals Research and Development Division as part of the Research and Development Center back in Saudi Aramco. So going back to your question, Dr. Ahmed, when it comes to scaling up chemistries that are done in the lab and trying to bridge the technology readiness level from bench scale, pilot scale, demonstration, hopefully to commercial deployment, there are multiple considerations that need to be understood. And it's great to have this audience, which has a mix between folks in academia and folks in the industry. Firstly, chemistry and chemical kinetics in general, it does not scale linearly, meaning that your reactions that are taking place in a small flask or in a controlled environment inside the labs it may not have the same phenomena when you scale it up at a larger scale. And we've seen this, which is why we invest heavily when it comes to scaling up and making sure that the data that we get is not only replicated at a higher scale, but it is also reliable. Another thing is heat and mass transport phenomena in general. It does not scale linearly as well. The heat transfer on reactions and mass transfer limitations may be introduced at a larger scale and observed even at that scale more so than you would see it at a smaller scale. And so you need to redesign your process, you need to redesign your reactor setup in order for that to be successfully commercialized. One important aspect is about process safety. So when you're in the lab, you're usually in a controlled environment with a minimum number of hazards that could be applicable within your labs. However, as you scale it up, the number of risks and number of hazards as well get more and more introduced. And so from an industrial point of view, we also need to ensure that we have a safety preparation, emergency response plan, and any risk mitigation measures that are put in place for successful demonstration of these technologies.
Thank you very much, Dr. Mohammed. So, Mr. Mohammed, for SCACSI, the concept of valley of death, I'm sure it has different implications, different measures. What's the risk appetite from an investment point of view, from risk-taking point of view? How do you decide on what kind of chemistries or technologies where you provide the investments across the entire value chain?
Okay, so I think this is a different spectrum. So as mentioned by the Dr. Amir on the kinetics and the process side of it, taking it from an investment perspective, I think the nature of our chemical industry is a capital intensive and also a time related. Takes long time until we have a validation and we have a ready product that can be deployed on a commercial scales. And this is where the lab and technical aspects comes, as well as the, say, venturing or commercial side comes. In SCACSI, we have our research and development where we are focusing on developing our existing portfolio and new application. And at the same time, we have our corporate venture capital operating and investing in new technologies. We need to understand that the way that corporate venture capital is operating and investing on those lab scale or even somehow a piloting technologies requires more capital intensive as well as requires more technical engagement other than the other type of investments that you require. If I recall back in the Valley of Death and having of chemistry and comparing the technology side as well as to our chemicals, then the typical duration to have a product that you can bring it into a market in the chemical world, it takes up to 10 years or 15 years until we have something that really can serve the purpose for this. On the other hand, on the technology, you can just deploy your solution within months or weeks. To recall Instagram, they just from coding till public, they just made it in 8 weeks. ChatGPT was back in 2022, and now here everybody is using ChatGPT. But when it comes to, let's say, methanol, we are a major producer of methanol in the region, and everybody is using the conventional way of methanol through reforming and synthesis here. On the other hand, if you want to touch base on the biomethanol, It is, though that it's been now commercialized, but not up to the scale of the conventional one. Simple example, the normal operating capacity of a methanol plant in a conventional way is a 1 to 2 million metric ton per year. And this costs you around 800 or $1.5 billion to build such a plant. On the other hand, for a biomethanol, you need nearly $500 million to build a 50 to 100 KT of biomethanol. So that tells you how, difference is the magnitude of investments and appetite, so you can go to whether changing to this new methodology or staying in your conventional way. It takes longer time till we reach to a maturity into the other biochemicals, but it will be there because as you are building your plants, you learn, you bring better cost to the next one and the following one. So this is in a nutshell.
So just a follow-up question. You mentioned from the development cycle, the potential investment, the opportunities, but how do you start with the funnel? So for example, there are, let's say from the R&D centers, you have 100 different ideas. Do you consider investment in all of them? Or do you prefer to have partnerships with the universities as a de-risking layer, for example?
Well, we are operating on both models. First of all, we do have our own ideas that we are adopting, and we have a stage gate to verify each process that we're going to, whether we validate that idea to go further for an investigation and development. And this is where it should go with the flow. And normally we also have more engagement with universities, and in order to see what are the new ideas that we can incubate or accelerate that's serving the purpose of our industry as well as our strategy as a company. Maybe recently we just signed a 5-year agreement with the KFUPM, research agreement, where we are going to have a list of potential projects from both sides, and that will help in picking up the one that fits the purpose for the company strategy as well as the KFUPM objectives in research.
Sounds good, thank you. Mr. Michael, you are one of the greatest minds we have within our building. I really want people to hear from you. You come with different expertise across different industries and different sectors, and you always have a different perspective about how to approach such challenging aspect, like how can we bring and translate technology all the way to the market. I know that chemistry intersects with many of the initiatives that we're working with. So if you want to assess a specific idea or a specific solution or a technology, what are the main, let's say, main points or milestones that you must see in a specific startup or specific early stage innovation to be able to implement it within your business or within your different sectors that you're operating with?
Assalamu alaikum. Thank you very much for the introduction, much appreciated. See, when you look at chemistry, it's slightly different. It doesn't change during the life cycle of an invention. You have to cover specific parameters of the investment right from the start. And the most important one is technical, how you actually develop your product and what is the innovation inside. The second point, and that's extremely important, regulatory. Chemical industry is highly regulated. And a part of the environmental regulation, you have to look at the entire life cycle of it. And last but not least, the market. Now, chemical industry is a highly concentrated market. You would not find a lot of startup companies coming with a great new product and then they can market it all over the world. That's just simply not happening. You have a number of established players and they have a market concentration of 80–90%. And you have a number of buyers. That's not a free market as well. So these 3 points, and they will go from the lab bench down to the scale, they have to be covered right in the beginning. It is not a journey of discovery, it's basically walking a proven path down the road.
Thank you very much.
In addition to that, just to add on that, You have to look at, and this was very much mentioned and well mentioned by both Dr. Mohammed and Mr. Mohammed, is the capital intensity. And I'm not talking about the lab bench part. That's up to $1 million. You can still cover that somehow with friends and family, if you have a good family and good friends. But then, piloting, totally different story. So when you look at the bulk of chemical inventions, they happen actually in a bracket between $1 to $30 million and plus $30 million. That's a heavy investment. And it is analog, usually. It's either winning or failing. Then, assuming your pilot goes through well, and you mentioned all the critical parameters which can go wrong in the scaling, so when you scale, the values are much higher. They start with 10 million if you have a high performing product in specialty. They go over $1 billion when you look at larger productions. So taking that all together, I think reaching out an early stage to funders, go through testing, show what you have. Not only focus on the science, but look at the entire picture. That's basically a value proposition which counts.
Thank you very much, Mr. Michael. And on relevant notes, later today, I think 2 sessions after our panel discussion, we have Dr. Halim Radawi. He will share his experience, distinguished professor, the co-founder of the Haran Techno Valley Science Park. And I think he has the first truly commercialized chemistry-based technology from KFUPM. So it will be very exciting to hear a use case about that kind of journey, the time it took, the kind of investments that's been placed. And it's actually way more. I think maybe Dr. Halim, 30 years of development. So yeah, we really look forward to hear the kind of journey and the kind of enablements we need to have. But one important aspect about enablement is relevant to intellectual property. We know that, for example, in all the R&D activities in Aramco, there's been an amazing work, a lot of solutions and technologies being deployed internally. Now there's huge momentum to spin off technologies. If I'm not mistaken, Aramco, they're sitting more than 15,000 granted US patents. From a strategic IP protection point of view, how can we, as an inventor, if you really want to file a patent for the potential of commercialization, how can you handle the protection aspects from the drafting the patent itself, the IP fencing moving forward? How can you protect your idea? And how can you ensure that this IP protection journey is an enablement rather than a liability?
All right. First of all, I want to be friends with your friends, Michael. So hopefully after this we can catch up. But going back to your question about IP protection and IP strategy in general, you may have an excellent idea, but it's also about timing when it comes to the filing. You may file your idea too soon, or you may file it as well too late. When you file your invention disclosures too soon, your idea may not be mature enough, and you may risk having your patent application declined because the novelty hasn't been proven, or you haven't really showcased what's different about your idea versus the prior art. When you file your idea too late, it may be considered as a missed opportunity, meaning that someone else could beat you up and beat you to it, and could file your idea before you do. And so that would be inviting some of your competition. And so it's really about finding that kind of balance, knowing exactly when you would like to disclose your idea. Also, you have to keep in mind that once you file it, it is only a matter of time until your filing would become public before it is even granted. So you need to also keep that in mind. Another thing that is also relevant in academia and in industry as well is filing with a partner too soon, before having some kind of a commercial assessment of filing that invention disclosure and being basically in a wedlock with that partner for that specific invention. So that could be risky if you are with a partner who may not be reliable, who may not help you with the scale-up of that technology and taking it all the way to commercialization. You mentioned a very important point, which is the ring fencing approach. One patent may cover a lot of claims, but then again, you want to make sure that you don't invite competition. With the ring fencing approach, you're able to cover all aspects of your technology in a holistic manner in order to protect your technology from different angles to make sure that your technology can stand on its own feet. While keeping away any potential competition. There are lots of different IP strategies. In academia, it's very important to also abide by technology transfer guidelines. That would also invite the potential corporate partners, make it easy to do business with innovators within academia.
Thank you very much. Mr. Mohammed, on a relevant point regarding intellectual property. Right now, I assume many of the R&D activities happening within the organization. I think right now, many of the organizations, they're looking into how can they potentially spin off some of their solutions into startups that can offer the service as a vendor, rather than trying to have everything internally deployed. So for those kind of organizations, what kind of challenges from a licensing point of view they would face? I know that some organizations, they like to have they never provide an exclusive license. Others, they just want to make sure that it's really, they want to maintain the control, rather than the whole world is moving toward how can we make it easy to be spun off and enable people. Like for example, KFUPM, even a certain organization, when they announced the 0-0-0 structure, 0% royalties, 0% equity, 0% fees, is mainly just to enable the commercialization of the IP. How corporates actually are dealing with this challenge?
Well, that's a very good question, and actually I'm living it today. I was 2 weeks back in our venture capital company in Switzerland, and I was talking to the director because we have our own technology that we're developing. It's a breakthrough in engineering plastics and normal plastics. And I was talking to him that we need to know what's the next level in terms of licensing, and also how can we manage being a licensor as well as a commercial producer to this technology, which is something new to SCACSI actually, and we're trying to figure out once we validate and commercialize this product. On the other hand, when it comes to corporate venturing, okay, and that's the difference between the corporate venturing and open venture, is normally corporate venture serves the purpose and the strategy of the company. So having a funding or a contribution to an investments or a technology and spinning it out, it's somehow not common in our industry, because normally we want to invest to a certain technology. Is something is either we want to acquire in the future, or maybe we can have it in a JV or a collaborative with our counterparts. Unlike venture capitals, where you don't see them much at a certain stage, and this is what I've seen in my personal experience. Normally, open ventures, they come at the very early stage of the technology, and they just want to run away. They would just sell it off or exit through selling it to Dow Chemicals or Exxon or SIPChem, SABIC, Saudi Aramco, any of those companies into this sector. The third one, which is very important, is actually the research entities and institutes at the places like universities and other research departments. We see, and this is one of the challenges, that some research entities or universities, they started to get out of their main purpose of being a pure research hub, to invite all the corporate and start acting like a corporate. Which is very challenging, because if I am going to invest in one of the research related to a certain technology in university, and I'm going to definitely contribute by either shouldering the cost of this research, if not all of it, and then I'm asked as a corporate to pay extra premium royalty to own this technology, or at least to use this technology for my own purposes, that makes the economics very challenging for me to enter into such a deal. And from here, actually, I would like to request all the research centers and universities is to have this under their radar, to focus on the research and bringing investors or corporate to fund such ideas and technologies and mature it, but they have to at least give a credit to the organization or the corporate who believes into this technology and can shoulder the cost just only to reach to a commercialization stage or make it a successful project.
Very nice. Speaking about venturing, Mr. Michael, when we talk about the manufacturing and supply chain integration by early stage ventures, how would you advise or consider in the chemistry sector when to consider, for example, localizing manufacturing, spending on the capex for manufacturing, versus when to partner to really take technologies forward to manufacturing?
Very good question. I think one of the main challenges is to look into the whole chain from upstream to downstream. I think one of the challenges that we experience in SIPCHEM is the moment when we started our polybutylene terephthalate plant, which is an engineering advanced plastic. The main challenge that we see it is this market serves automotive industries, electronics, high-end ones, where actually we don't have this downstream is matured already in the country or in the region as well. This has forced us to sell it as a resin, which is in a business model is not a lucrative one, because normally for an advanced engineering plastics, you need to have a conversion that can serve that. And beside the conversion, so if I am competing with a company like BASF, whom they have Mercedes-Benz and they have BMW just next door, and I have to send my material, that doesn't make it a successful business. On the other hand, so for this, we need to be very selective in terms of the raw material accessibility, because not all of these things has just a natural gas or sales gas as a raw material. It's actually more of a mid or end of chain chemicals as a feedstock. We need to make sure that our existing market at least can absorb some of this product. And as well as we need to ensure that a proper infrastructure of supply chain. Today, I'm just only counting on shipping, railways, and other purpose of supply or logistics need to be a little bit more matured in terms of that. Another example for you need to be also to understand what is the dynamics of the market, in order to make a decision whether you go for that technology or you have this industry deployed, and so you can have a sustainable. It also encourages the investors to invest in your project or in your technology if they get a comfort that there is a reliable raw material supply is available, and there is at least a fixed market has been granted for decades. That's the...
Thank you very much, Mr. Mohammed. So, Mr. Michael, similar question on manufacturing and supply chain. I know that you have one of your recent businesses that you're bringing to the Science Park. It's relevant to advanced manufacturing. So, for early stage ventures, what would be the main challenges when it comes to focusing on the manufacturing and supply chain aspect? How can they really take some considerations like when to invest in the capex? And what's the role of emerging tech, like with the AI and all of the new technologies that are coming in to shorten the development span or provide some sort of easiness to the complexity of the entire process?
Got you. So I think looking at funding, and that's basically the major point, in early stages, I believe the best is to go for grant funding that can either from the university itself, you have multinational organizations, cross-border, prize money. That's basically the money you need in order to get your innovation going. And then at one point of time, if you have data available which can be brought, you have your TRL ready, benchmarked to existing frameworks, then I think it's time to reach out to venture capitals. And they are usually independent venture capital. Like Mr. Mohammed said, they run away, but actually their mission is to run away after a certain time because their goal is purely financial. So they're going to inject money, and usually they are coming in a consortium. You can look at that stage when you need 1, 2, 3, 5 millions. That's a combination of different independent venture capitals. They all come in between 5 to 15, 20%. You rarely find a lead investor in that segment, but they bring networks. So they take you from one spot to the next spot. They bring in financial discipline, and they bring in access to markets in terms of data, not really in terms of market access. They can also, at one point of time, if you have enough data to prove, basically bring the more patient money on board, which is corporate venture capital. And this is where the music really starts to play, because they are used to bigger tickets, but they come at a much, much later stage. You have to have really solid data to show that your innovation is a real innovation and that it can be translated into real life. Now, taking that all together, that's a proven path, it's a beaten path, and it worked, because you're looking at a long cycle industry. So the market cycles in chemical industries are long cycles. The innovation cycles are even longer, because at one point of time, when you go for the final card, you have to prove basically long-term data, performance data, and they are 1 + 3 years sometimes, in order to have that segment. And you need to come with an entire life cycle assessment. So that's not only showing that your process, your product is better, you have to show that the feedstock is available, you have to show that the environmental conditions are actually kept and keepable, you have to look at the waste management, and once the asset is basically squeezed out, utilized, you have to show what happens with the remains. And that's something where you can really walk down a beaten path and bring your innovation to life.
Thank you very much, Mr. Michael. I have a lot of questions. I'm enjoying the discussion, but I know that we are limited in time. So maybe we would like to open the floor for questions from the audience. Anyone has a question? I think we have the mic somewhere.
Thank you very much for your informative discussion. Just I have a question about the challenge related to some chemicals that need to be used in oil and gas reservoir. What we can see that development of these chemicals usually done at lab condition. But when you take this chemical and you wanted to make deployment in oil and gas reservoir condition, under harsh condition of salinity, temperature, pressure, so on and so forth, these chemicals like surfactant, polymer, scale inhibitor, corrosion inhibitor, they failed. You know, how we can make the right environment to mimic or develop a new version of chemicals that can sustain this harsh condition and make good work for improving oil recovery.
Sure. Well, we're now in the digital age, and so we need to also use the new tools that are at our hand with AI, ML tools. Not only are they helping us when it comes to the ease of replication and automation of experimentation and processes and so forth, but we also need to take advantage of coupling that with high throughput experimentation, and at the same time using AI ML tools to discover new materials, new compounds that could withstand those conditions. This is something that we do at Aramco, and we take that, couple that with our capabilities, invest as well and scale up infrastructure. One example is our Petroleum Conversion Research Center, which was mentioned in today's opening remarks. So that requires a lot of investment when it comes to the infrastructure. So whether it was infrastructure that was physical in terms of equipment, in terms of personnel, training, and so forth, or digital infrastructure, taking advantage of all of these new digital tools that are at our hand, and making sure that we can discover new compounds and new materials that may have not been discovered before or have never been tested for these applications.
Thank you, Dr. Muhammad. Any other questions? One question in the back.
Thank you. I'd like to know what percentage of startups fail, and what is the major reason for the failure of startups?
Please take.
Well, normally startups is a very high risk investment, comes with a high returns. I don't have a certain percentage of failure. But I think one of the reasons that why startups are failing sometimes, from technical perspective, sometimes the same the people who's working the projects, when they start scaling up their research or their development of whatever the projects that they're working on, they tend to forget that the change in the atmosphere around them as they are scaling up. And when I say this, is either related to the technical side of it, despite the nature of the chemistry that they are working on, and sometimes the deployment and the of the technology itself on a larger scale with the change of the surrounding environment of it, be it the engineering of the equipments, be it the way they are operating the facility. These are the things that could put the investment in a financial crush, and then later on could fail to continue with this investment.
If I may add on as well, is an important aspect to consider for startups and innovation in general is the industry ready, and would it disrupt any existing infrastructure? Do we have a seamless integration with the industry, with the infrastructure when we introduce these new technologies and new chemistries in specific? That's one. Another aspect which Michael touched upon is when it comes to the supply chain itself. So the ease of the establishment of the supply chain can be a major bottleneck for new technologies. So new ideas, they come in handy, and there are lots of people who are very smart who could come up with excellent ideas, but the availability of the materials needed to make this idea viable, the transportation, the storage. So all of these aspects need to be taken into consideration. So while we always talk about technology readiness level, we also have to talk about commercial readiness level. So is there economic viability for that specific technology? And if so, are there any environmental impacts that this technology could bring in when I integrate it within the system around it?
Yeah. So I can get you from a certain window angle some numbers. If you look at an independent venture capital company focused on chemical industries, they screen, let's say, 100 proposals. Out of those 100 proposals, they might invest into 10. Out of this 10, and that's again a rule of thumb, one succeeds and makes all the money. 2 to 3 generate IP, which can be used, sold, or otherwise distributed. 7 of those basically never see the light.
Thank you very much, Mr. Michael. I just would like to add, from an ecosystem perspective, I mean, I really appreciate all the insights, but I just want to add to it. Currently, for any startup to succeed, maybe you already know that like 1/10 of the startups typically succeed, and in the hard tech sector is even 1/3 of the 10th. But we've seen examples of ecosystems where they really integrate all of the enablers effectively, that they manage to get much higher survival rate. And that's actually what an active ecosystem requires in the deep tech sector, areas like chemistries. We really need the agile funding from the very early stage to navigate through the R&D valley of death, the commercialization valley of death, and then even the commercial translation valley of death. The specialized infrastructure is very important. We've seen technologies that it's developed in the lab, but you don't really have the infrastructure to do the scale-up or the piloting and deployment. And that could be a bottleneck by itself. You really need, on top of it, the access to the market. Many technologies who are really trying to operate as a technology push to the market really become very difficult to take it there. The market pull is very important. The alignment with the market need is very important. And I always believe in that slogan. They say it takes a village to raise a child. It really takes a country, like a very healthy ecosystem, to raise a deep tech startup. So yeah, thank you for your question. It really taps into many of the challenges that we're trying to achieve. I think for the sake of time, maybe we can have one last question, and then I know that Dr. Bashir wants us to wrap it up.
Can I ask a question? Very nice discussion. Thank you. Good afternoon. My point is, at what point industry just lose their interest? Like there is a lot of innovation in the lab. We are developing new technologies. But at what point industry thinks that, no, we cannot do this, or this is too ambitious? Or sometime, as you have mentioned, that there is life cycle assessment. So as you know, we develop different models for that. But for that, we need real-time data for industry. But due to, I think, their intellectual property or their industry secrets, they don't want to share everything. So my question is how this all together stands. At what point industry thinks that, no, we cannot integrate this, or this is too difficult from industrial point of view. Thank you.
Take this honor.
Thank you.
Sure. I guess it really depends, really. And when it comes to academic research, it is for the pursuit of creating a new science and making new discoveries and so on and so forth. But then when you compare that with corporate research, it is really about how can we create value from those new scientific discoveries. Yes, there is always, we try to draw the line when it comes to if that is too ambitious or not. But it comes to the commercial and technical assessment. So can the technology, is the data that has been generated, does it have the efficacy, the efficiency, the reliability to be replicated as well? Can this be scaled up? Do we have the scale-up apparatus and the long-term testing that proves that this phenomena and this technology actually will work in the real world? That's a first thing. But the second and most importantly is from a commercial aspect. There are always volatility when it comes to the markets. And so we need to keep that in mind, and the ease of the establishment of that supply chain. Can we, if we decided to invest further and deploy that technology, will we be able to source the material for large-scale deployment and wide deployment, not for one specific field? So we need to keep having these conversations in between academia and the industry. It's also very important that academics, they retain their rights to teach, to publish results and so forth. So there are always gives and takes between the industry and academia, in which we need to continue having these conversations and really understanding the challenges that the industry would need, and how can academia bring in these new ideas that could make it into commercial deployment.
Thank you very much, Dr. Muhammad. Thank you very much all for attending the session. Thank you for the panelists for the insightful discussion. We'll be around. Feel free to connect with the speakers if you have additional questions, and really looking forward to the follow-on sessions. Thank you very much.
Welcome back, everyone. I will now introduce our keynote speakers, starting with Dr. Ghaythan Al-Muntashiri. He is the director of the EXPEC Advanced Research Center in Saudi Aramco. Dr. Al-Muntashiri is a leading figure in petroleum engineering, having pioneered advancements in production technology by developing innovative fracturing fluids and cross-linked gels for high temperature and high pressure well environments. As a director of EXPEC, he oversees upstream R&D strategy for Saudi Aramco, including 9 global research centers. He was awarded the SPE Distinguished Service Award in 2022 for his devotion and contributions to the Society of Petroleum Engineering and the industry. Please welcome Dr. Al-Muntashiri.
Thank you very much. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Ladies and gentlemen, dear colleagues, good afternoon. I'm very delighted to be with you today and to present at this prestigious conference. Before I start, however, I would like to congratulate the Saudi chapter of the American Chemical Society International for putting together this impressive program. Congratulations. I understand this is the first time we hold such an event in the kingdom, and it's really pleasing to see this. Each time I come to KFEPM, it brings me a lot of great memories, where I started 30 years ago as a bachelor student here at the Chemical Engineering Department. I'm a very proud graduate of KFEPM. I always enjoy my visits here, where we meet colleagues, we meet members with whom we have either business or we have great memories when we used to be in classes together. I also have the pleasure of meeting some of the members from whom we have learned, teachers that were giving us classes for whom we are very grateful. Today I would like to share with you a topic that is not only important for the company, for Aramco, but also important for the country, and it's also close to my heart. Oil field chemistry is a topic that is transforming upstream operations to bring value, to bring the best out of the chemical molecules for our oil field applications, when we make chemicals for applications in the subsurface, in areas that we cannot reach and we cannot see. The presentation today will have 3 parts. First, I'll talk to you about our organization, the upstream R&D arm of Saudi Aramco. After that, I'm going to talk to you about some examples of the technologies that are developed by our brilliant chemists and scientists across the globe. Last but not least, we'll share some light on what it takes to make these chemicals successful from the lab, from the synthesis phase, from the controlled environment, from the beaker scale, all the way to the large field scale, where we pump thousands of gallons of these chemicals in the subsurface. So let me start first by talking about EXPEC Advanced Research Center. We are an organization that has a very ambitious and bold vision to be the world's leading institution for upstream R&D, creating reliable and sustainable technologies. And our mission is to support the upstream business of Aramco by advancing innovation, maximizing value creation, and accelerating the transition towards net zero emissions. So the topic today, as I said, is a very important topic. It's an accelerator that embodies that mission. Oil field chemicals extend the reservoir life, they reduce the carbon intensity, and they translate science into economic and environmental value. Our organization has global footprint across the globe, from Beijing on the map that you see in the east all the way to Houston in the US in the west. Each center that you see here is strategically positioned to address specific research needs where we do research around the clock. Every day, our organization, every calendar day, in fact, over the past 3 years, we have been producing at least one patent. Behind every breakthrough, there is a dedicated community of researchers driving the innovation forward. And here, as you can see in this slide, XPEC Advanced Research Center, or XPEC for short, our strength is in our people. We have a diverse team of almost 800 professionals with 133 PhD holders and 59 master's degrees holders. We nurture this talent through internal programs. And the reason for me to share this is because we wanted to shed light on the important pillars for an R&D organization. In XPEC, we celebrate two things: business impact and technical excellence. And none of this would come without the right people in place. And for that reason, we have the Aramco Academy of Leaders with Innovative Minds, or ALIM for short. For those that are non-Arabic speakers, ALIM means a scientist in Arabic. And this program nurtures our talents, help them grow and develop their skills. And our vision, inshallah, is that one day we will have a Nobel Prize winner from XPEC. The second pillar that we look at is the technical excellence. And this is what we see here. As you can see, we have what we call the deployment badge. So whenever somebody takes a technology to the field and then it gets tested successfully, then we go to their office and then we hang these badges. And this is a recognition of the business impact dimension. For the youth, we have the Research and Development Program, which is going to equip our researchers with the tools that they need so that they become the future alam. It teaches them project management, communication, looking at the business case of all of the development projects that they embark on. Our organization in numbers, we are a proud organization that have had a lot of contributions to the scientific community. We enjoy a wide recognition. So far, our organization have over 2,500 granted patents. Not only that, our organization is well cited in literature. We have over 1,800 papers that have been published in technical and peer-reviewed journals, more than 5,200 that have been published in international conferences. If you look at the citations, we are almost at 13,000 citations. It was a moment of pride for all of our members in XPEC Advanced Research Center when the annual Stanford University ranking report was published. It ranked 2 members from our organization to be among the top 2% cited scientists. Our organization is handling a diverse portfolio. Within this community and within this large ecosystem, our research spans from subsurface modeling that you see on this slide to robotization and sustainability. Yet, oil field chemistry is the silent and quiet but extremely powerful pillar of this strategy. And for that reason, I'm going to share with you today where the applications of oil field chemistry fall in our upstream oil and gas business. The science of chemistry comes across all of our operations. We have developed a spectrum of innovative chemical solutions where we use them in drilling, well completion operations, well stimulation, scale, and water control at the subsurface. And I will share with you now a few examples where we shed light on applications of scientific advances in chemistry to bring technologies from the lab scale all the way to the field. And as I go through the slides, there will be this will be part 2 of the presentation, and there will be a barcode in every slide where you can feel free, please, to scan it and link to the papers that are related to that specific technology that I will be talking about. So starting with the drilling applications, we do that safely and efficiently. by eliminating organoclay, which was an additive that we have in our drilling fluids. We produce a non-damaging oil-based mud that prevents stuck pipe. This improves the lubricity of the fluid. And if you look at the picture that you see here, this is a viscometer that we use in the lab to test the rheological properties in response to the addition of certain additives. This was done in our labs, and we were able to test this, and we improved the rate of penetration, reduced the stuck pipe incidence. The second example that I would like to share is the geopolymers. This geopolymer cement replaces the typical Portland cement with low carbon inorganic polymers that are made from industrial waste. It enhances the mechanical strength of our cement and reduces CO2 emissions by up to 80%, a perfect illustration of our commitment to sustainability. The third example is related to the post-drilling operations. After we drill, we go and stimulate the wells. And we use the powerful science of chemistry in this area to develop materials that can dissolve the subsurface rock structures so that we enhance the deliverability of the wells, or in petroleum engineering language, we enhance the permeability of the reservoir. And the low viscosity acid system offers a single phase and a great example of a technology that we developed that was able to produce more oil and gas from our wells. And this was done also in our labs. And if you are wondering about this picture, this is a core picture, which is a sample of the rock in the lab, where we used this sample to treat when we use this sample to test the fluids that we developed in our labs, and we look at the impact of the chemistry itself, on the impact of the temperature and the reaction kinetics on the dissolution power of this rock so that we can produce more oil and gas. The other example is another stimulation fluid. Here we used the power of nanotechnology to produce more stable emulsions that can go up to 300 degrees Fahrenheit. This allows us to treat deeper reservoirs that have higher temperatures and improve the penetration rate of the acid, and therefore help us enhance the permeability, and therefore produce more oil and gas from the reservoir. When it comes to CO2-based fluids, as you know that the CO2 is the topic of the net zero transition, and this has been always in our radar when it comes to our R&D. If you look at this slide here, you see a picture of a test tube, or a graduated cylinder, to be more specific. This is where you see a formed fluid that has been made out of CO2. So we are using CO2 to help us generate formed fluids that are easily pumped, and they are also more effective because they are easily flown back compared to conventional fluid systems. And this was able to, in fact, to save us some water, because if you use CO2 to generate foam, you avoid the consumption of extra water resources. In this field trial, we were able to save around 500 barrels of water and utilize 200 tons of CO2 where they were injected into the reservoir. When it comes to scale and corrosion, this is another area of major interest to us in the subsurface. We begin with one of the most persistent field challenges here, which is the iron sulfide scale. This restricts flow and it damages equipment if it forms on the pipeline itself or at the wellhead. Our custom designed fluid, which is the iron sulfide dissolver, it was able to help us restore well productivity, achieve up to 50% increase in gas rate, 700% in oil rate, and 34% improvement in water injectivity. Yet, enhancing flow is only part of the story. We also need to manage what we produce from the reservoir. Water is a great resource, but in some cases, we don't want to produce it. Therefore, we also have an interest and a focus to work on chemicals that are used to reduce the water production, and one of them is the nanosilica that you see here in this slide. This is a technology that was designed in our lab. 10 nanometers of particles were used to consolidate and to gel only when they reach the target zone in the reservoir. So we inject them as liquids. As they get pumped into the reservoir, with time and temperature, they react to form a solid gel. And this gel was able to reduce the water production from our wells and therefore avoid the extra water that is being produced to the surface. This helps us save energy and reduce the capital investments of water handling facilities. Arc resin is a unique chemistry that was used to handle the wells that have what we call casing annulus. This is the case when you start flowing fluids, not from the well bore itself, not from the well tubing itself, but from the cement due to cracks. And this is the case. This case has been treated with the arc resin. It's a chemical that we inject from the surface, and then it was able to penetrate through these tiny cracks and seal them forever. Now, I would like to move to the third part of the presentation, which is shedding light on what it takes to be successful. If you are a chemist, if you are a student, if you are a researcher in the lab doing experiments in a controlled environment, how would you scale it? How would you think about it to move from the lab scale all the way to a field application for the upstream business, where you can pump the fluids in thousands of gallons instead of a few milliliters? This will be a summary of our experience in our R&D organization. So first, you need to worry about the specs. You have to have the right, clear, specific targets in terms of performance for the fluids that you are testing. If it's a water control chemicals, if it's a fracturing fluid, if it's a polymer, whatever performance, you have to be specific about it and you have to design it accordingly. And these specifics or these specs will not come from vacuum. They have to come from the field data that you have access to. The conditions, reliability under near reservoir condition is going to be also another factor that you need to think about. Are you injecting it to stay there forever? Are you injecting it to come back? That's when you start linking the performance properties to the chemistry that you are designing as a chemist. The magnitude from the lab to scale, scalability. You heard in the previous panel a lot of interesting discussions. You need to think about the chemistry that you are using. It has to be something that can be scaled up, where you can bring the volumes to the field in a reliable and in a smooth manner. The cost, of course, is always a question. Always benchmark with the existing technologies, not only in terms of performance, but also in terms of cost. The cost has to be somewhere comparable to existing technology so that you give your technology the advantage of being used. We understand sometimes when you design a chemistry for the first time, there will always be extra costs, and this is fine, as long as you keep in mind that with the mass production of the chemicals, you will be able to compete with the existing technologies, and the performance of the material will outweigh the extra cost, if any. So what are we going to do if we are designing a field trial for the first time? From our field experience, the successful deployment of chemical technologies, it demands discipline. In the field, these are large operations. They are complex. It's exactly an experiment, similar to what you do in the lab. However, it's an expensive experiment, and for that reason, there are multiple things that need to be done. You have to look at the compatibility of the fluids. You need to look at the performance of the material. You need to look at the testing protocols so that you ensure that you do the best you can in terms of testing and test everything you can do in the lab. Also, it's very important that you pay attention to the quality control of the chemicals. You test chemicals in your lab in a beaker. You bring them in the volumes of liters or milliliters, and you bring them in small bags in the kilograms. But when you go to the field, you will end up with mixing thousands of gallons. And here, literally, you're talking about loads of multiple trucks of chemicals. You have to ensure that you have the right QC protocol so that you ensure that whatever you receive in the field is similar to what you have in the lab so that the performance is going to be the same, hopefully, inshallah, and you end up with the right successful field trial. In closing, as we look at the future, I believe that the oil-field chemistry will remain at the heart of upstream innovation, and I think it's not only going to improve the efficiency of our operations, but it will also improve the local economy and adds to the knowledge-based economy that the country is hoping for, inshallah. Through collaboration, digital transformation, and a relentless pursuit of excellence, we are building an ecosystem in Expect Arc around us where science meets sustainability and where innovation fuels the future, inshallah. We are working with academia. KFUPM, of course, is among the pioneering institutions that we are working with to improve oil recovery and to produce materials that are going to be outperforming others, inshallah. Together, our scientists, engineers, and partners across academia and industry will all share a single objective, which is value creation. With that, I conclude my presentation, and I will be very happy to answer any questions that you may have. Thank you.
Thank you, Dr. Ghaythan,
No
for your
problem.
inspiring talk. I kindly request Dr. Hassan Baqil to join us at the stage for the trophy. Our second keynote speaker is Dr. Halim Hamid Radwi. He is the ex-senior advisor to the CEO DTV. Dr. Halim Hamid Radwi has been senior advisor to the CEO of Dhahran Techno Valley Company since 2022. He served as interim CEO of DTV from 2012 till 2016 and vice president earlier. He is a distinguished Saudi chemical engineering leader and a professor of chemical engineering department here at KFUPM. He is recognized with a citation of excellence from the United Nations Environment Programme for pioneering research on UV-induced polymer degradation and ozone depletion impacts. Since joining DTV in this advisory capacity, he has guided strategies to expand the Dhahran Techno Valley ecosystem, fostering university-industry collaborations with global tech firms to drive R&D in digitalization, quantum computing, and sustainable materials, supporting over 18 partner companies aligned with Saudi Aramco and Sabic Need. Please join me in welcoming him.
Assalamu alaikum. It's an honor to be in KFUPM and present this presentation on successful development and scale-up of refining technology, value of collaboration and partnership. Thank you for the introduction. Okay, so the agenda of today's presentation is the introduction, value of collaboration and partnership, refinery conversion processes, family of FCC technology, the fluid catalytic cracking, HSFCC, which is high severity fluid catalytic cracking features and novelty, comparison with other technologies, and the summary. I'm just representing a group of people who contributed in making this dream true by commercializing the technology from lab all the way to commercial plant, going through pilot plant, demo plant, semi-commercial plant, and eventually a commercial plant of some 96,000 barrels a day in Korea. There was a team working from KFUPM. I have one member sitting here, Dr. Muhammad Abul Hamail, plus Abdullah Itani, Dr. Abdullah Itani, if he's here. I don't see him, plus Dr. Maad Allah Yarhamu, and other UPM members, as well as Aramco personnel and a group of Japanese working with us. The main drive for developing the HSFCC was twofold. First is to maximize the production of light olefins, particularly propylene. And the second one is to use the low-value heavy oil, which is vacuum residue and vacuum gas oil. You can see on the right the plant, how it works. The feed is VGO, which is vacuum gas oil, going through the HSFCC plant, and all these products coming out, with the primary product being propylene. The value of collaboration and partnership in HSFCC is very important. Universities, by their nature, are not supposed to work on technology, the core business being teaching, research, at the most startup, but going to the commercialization of a certain technology of this scale needs to have an industrial partner. So if you see, the collaboration has contributed the development of a scale-up and commercialization, starting from KFUPM, Research Institute, and it was both the researchers and the faculty members involved in it, Saudi Aramco. Without Saudi Aramco, it would not have been possible to really lead this project. And the INEOS. INEOS is a Japanese company which keep on changing the name. We started with Nippon, then it became Mitsubishi, then became JX. Recently, it is INEOS. And if you look into a lines, these are the lines: KFUPM, Saudi Aramco, and Innovators developed the technology, and the two partners are Accents France, who are the licensor, and Technip Energies do the licensing, these two companies. This is the picture which I always admire, which brings together the Japanese scientist, Saudi scientist, and Aramco scientist. And you can see them all with the previous rector of the university, Dr. Khalida Sultan. Talking about the process, fluid catalytic cracking is a commercial process to play an important role as a gasoline producer. So the maximizing the gasoline is what FCC is all about, either from RFCC, which is a resid FCC, and the DCC, which is a deep catalytic cracking, which we have in Petro Rabigh on the western coast with Sumitomo, and then R2P resid to propylene, and high propylene FCC produced about 10% propylene from distillate feeds. HSFCC high severity is unique because it takes the low value VGO and produces about 20% propylene along with other lighter ends. This is how the FCC technology maximized propylene production, starting from HSFCC, deep catalytic cracking, and resid to propylene. And you can see the feed is heavy residue, light residue, vacuum gas oil, and high H content VGO. The FCC units in Saudi Arabia, being the producer of gasoline, are in 3 different refineries. The first one is Samraf, which used to be a collaboration with the Exxon Mobil, previously Mobil when they started, and then Exxon Mobil. and Saudi Aramco in Yambo. This was about 90,000 barrels a day. At that time, this was the largest FCC unit in the world. I don't know what is the status now. Then there is a Sumitomo plant in Petrorabik, which utilized the deep catalytic cracking, DCC, about 92,000 barrels a day. It's a joint venture with Sumitomo. The technology used is Sinopec and Technip Energies. The last one was Saudi Aramco Total Refinery, Satorp in Jubail, which is a lower capacity, and it is HPFCC, high propylene FCC. This, and as I mentioned, this was a collaboration between Japanese, Saudi Aramco, and KFUPM, and it has got a patronage from Mr. Ali Naimi, minister at that time, and you can see Dr. Abdulaziz Al-Dakhail, the KFUPM former rector, Allah yarhamu, and Dr. Bakr, Mr. Ali Muharib, Japanese ambassador, Dr. Ino, who was the project manager from Japanese side, and myself giving the presentation. And what is HSFCC technology? It is basically a turned FCC process upside down. Normally, a conventional FCC is a riser. This one, HSFCC, new technology was introduced, which is a downer to maximize the yield of propylene. It uses commercially proven FCC technology hardware. It retrofits of existing FCC, except that you have to change the configuration of a reactor from riser to downer. And then it offers refinery petrochemical integration opportunities. HSFCC is not a standalone unit. It has to fit in the refinery and the petrochemical complex, where there is a feed available, VGO or resid, and a product propylene going to a polypropylene plant. That's why the first plant came into a petrochemical plant, and the second one is also coming into a petrochemical plant. None of them is in Saudi Arabia because the configuration doesn't fit in. It demonstrated VGO and resid feedstock in a commercial plant, and available conversion extraction technology for C2 to C5 streams from FCC can further enhance adaptability. Again, the features of HSFCC technology is the catalyst system involving ultra-low hydrogen transfer. And this was designed with high selectivity to light olefin, targeting to propylene. And then the reaction conditions for high propylene and butylene yields at high severity at 600 degrees C, which is very high temperature, and high catalyst to oil ratio of 20 to 30. Downflow technology is mandatory to avoid catalyst backmixing, and maximize selectivity with ultra-short residence time is required so that the overcracking doesn't happen. This is how the journey of collaboration and the process take. It started back in 1996 with the pilot plant unit of 0.1 barrels a day in a garage in KFUPM, converted into this pilot plant facility of 0.1 barrel, and then it scaled up to 300 times to 30 barrels a day, which was not possible in universities. So we approached Saudi Aramco for this, and Saudi Aramco was generous enough to provide us the land in Ras Tanura. If it was not for Saudi Aramco, we would have never moved from pilot plant of 0.1 barrel to 30 barrels a day. Thanks to Saudi Aramco, Ras Tanura management, as well as the management in Tehran. The demo plant was a capacity of 30 barrels. The trial runs were conducted between 2001 and 2004. And then we move it to Japan, where the semi-commercial plant was built in Mizushima refinery with 3,000 barrels a day, about 100 times of the plant in Ras Tanura. which was in INEOS plant. And then we moved out. Then we were ready to commercialize it. We went through a tedious process of selecting the licensor among Exxon, the UOP, ExxonMobil, Chevron, and the jointly alliance team selected Exxon for this purpose. And the first commercial unit came into production in 2019 in Onson refinery in South Korea called S-Oil. The objective of HSFCC scale-up was to process, or basically to provide a gap between lab scale and industrial application. But the journey is very long: pilot plant, demo plant, semi-commercial, and then you go to the commercial plant. A lot of learning in it, not only technical, but there are legal issues involved, the negotiations with the licensor. Quite a learning curve. Now, the process demonstrated operability at all stages. It could have bogged down at any stage, whether it was a pilot plant in KFUPM or a demo plant in Ras Tanura, but the results were, alhamdulillah, favorable. The yield, the selectivity, the thermal stability, all were favorable. So the operation of the scaled-up unit was a key element to the process application, allowed the risking the last step of the scale-up processes. This is the breakthrough of HSFCC technology, key performance of downflow reactor, and these high conversion, 86.1% via high reaction temperature at 610, high selectivity. And if you look into the right-hand side and compare it with the conventional FCC, it has back-mixing issues solved, overcracking resolved, and the HSFCC came out as a winner to produce propylene. Site and Verne type catalyst separators are used. These are cyclone separators designed. By the way, there are a number of US patents and Japanese patents which were generated out of this project. And the inventors are from KFUPM. And it so happened that the first patent from Saudi Arabia was awarded by King Abdullah, Allah yarhamu, in a Wasam, Malik Abdulaziz, and Dr. Abul Hamail was the one who got that Wasam from Malik Abdullah along with other team members of KFUPM. Not only Wasam, there was 100,000 riyals also given to each of the inventors. I was not among them. Distribution of catalyst and feed, not only the patents that they came out, also the co-op training, the summer training, because the lab was in UPM, a lot of students, master's thesis. I don't see Dr. Eid al-Mutari, who is now a faculty in chemical engineering, did his master's thesis with Dr. Abdullah Sheikh on this process, and then he went to Texas A&M and got his PhD. The distribution of catalyst and feed was very successful in this process. Now, if you compare it with HSFCC performance and other technologies, you have 4 technologies, basically the conventional FCC, the one we have in Yamba, and the high propylene FCC, DCC, and the HSFCC. Deep catalytic cracking unit comes close to HSFCC in terms of propylene production and in terms of lighter olefin. The gasoline produced, we have to make a compromise on gasoline, but I think the refiner knows that they hate to compromise on gasoline. But the advantage here was that it was a high octane gasoline which can be injected into a gasoline pool to increase the octane number. This is the commercial unit in Korea. It's a huge plant, and you can see the height, which is because of the downer reactor that this has been employed. In summary, academic and industrial collaboration coupled with the great efforts of the faculty, members, researchers were behind the successful development and commercialization of HSFCC process along with the research team of Saudi Aramco and Japanese INEOS or Nippon at that time. Technology is capable of converting both light and heavy feedstock, which are low value, sometimes negative value, to unravel propylene eel without any recycle. Severe operating condition. The startup of the first HSFCC commercial unit was a real success in Korea, and all of us were very proud of it. KFUPM is very proud of having the first commercial technology with the high capacity, with the high rate of return, and very good environmental aspect which were considered at that time, 2019. Process flexibility offered refinery petrochemical integration. With liquid to chemical flourishing more, HSFCC units are expected to be licensed by Exxon and Technip. Very recently, the second HSFCC commercial plant is planned in Yutong refinery in China, and this is going to be also a very high capacity. The design is complete. I think it's still confidential before it is announced. Thank you, ladies and gentlemen. I'll be delighted to answer any query do you have for this presentation.
Thank you very much, Dr. Halim, for that insightful and valuable presentation. At this point, I would like to kindly request Dr. Hassan Baqil for the trophy and appreciation to your contribution. Now, it's my pleasure to welcome our next keynote speaker, Mr. Abdullah Al-Ali. Mr. Abdullah Al-Ali is currently working in NIDC as Chief Advisor in Pharmaceuticals and Biotechnology segment. NIDC is a government entity under the umbrella of MIM, which is the Saudi Ministry of Industry and Mineral Resources, with the main role of business development for specific industries in Saudi Arabia. Let's extend a warm welcome and attentive hearing to Mr. Abdullah Al-Ali as he delivers his keynote address.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon. It's always great to be back here at KFUPM. As Dr. Ghaithan mentioned, floods of memory really being here 30 years ago and coming back to deliver a speech. The last time I was in auditorium at KFUPM, I was having an exam, so I'm lucky now. There is no exam. Bye. Today's topic is about the landscape, the pharmaceutical landscape in KSA. And it's pretty interesting to know that, a chemical engineering degree or even a chemistry degree is perfect to do in industry. So rest assured that what you are studying here is perfect for the real world. I have 4 main sections in the presentation today. First, I'm going to talk about the national industrial strategy. And second one is the pharmaceutical landscape. Third one is the problem statement. If I also were to say it's area of improvement, it's not problematic, but I think with the support of KFUPM and other researchers, we can improve a lot on that segment. And at the end, we'll talk about the incentive that's offered by the government. It doesn't have equations, it doesn't have unit operation, it's very simple presentation, everyone to understand. I'm gonna start by an overview of the NIS, the National Industrial Strategy, that has been launched by His Royal Highness the Crown Prince back in 2022, and those have very, very ambitious targets when it comes to export, when it comes to increasing the GDP, tripling the GDP, doubling the jobs, also increasing the industrial output. And I'll be very honest with you, we all know that the legacy of oil and gas in the country, I don't want to upset anyone from Aramco or any other petrochemical processes, but the economy has been dependent for a long time on oil. And with the cyclicality of oil, as we're experiencing now, 60s, then you don't want to ruin your whole economy. You want to keep it sustained. And that's why there is, I would say, a need to have a non-oil driven economy that's not affected by the cyclicality of the oil process. And the pharmaceutical is a perfect example of diversifying from oil to a non-oil driven economy. Having said that, the NIS has classified the industrial sector into 10 main sectors. Of course, starting with the chemical, renewables, machinery, equipment, food processing, building material, metals, and so forth. When it comes to, the macroeconomic impact or the economic impact, definitely the petrochemical is a winner because we have a huge output of the petrochemical processes, whether it's in GDP or even in employment. However, when it comes to national security, I can argue that pharma is one of the top, if not the top sector among those sectors from national security perspectives. I'm highlighting also the chemicals stream because we're going to talk about the chemicals, value chain leading to the pharmaceutical, or the pharmaceutical going backward to the basic chemical streams that we all have in the kingdom. Okay, going to the pharmaceutical market overview, it's a huge sector. It stands at almost $1.5 trillion as a whole globe market size. If you deep dive into the Middle East and North Africa, it's 34, and Saudi Arabia is 13.2 billion. It's huge. So Saudi Arabia, with a population of almost 30 million people, we have the biggest market size in the whole Middle East and North Africa. It's appropriate to define first the conventional pharma versus the bioceutical pharma or the large molecules. For the sake of today's discussion, we're talking about classical conventional pharma, which is derived from basic chemicals. We're not going to talk about the large molecules or the biologics because, it's a different topic, it's a different animal. However, by growth, they are much higher than the classical pharma, but by volume, we're talking about a big portion of conventional pharma. And it will stay there for a long time because there are so many countries, not only in the Middle East, but also in the Africa and also other bunch of countries that they cannot afford biopharma because it's very expensive. But going to the conventional pharma, it's affordable, it's classical medication that we all know. For example, the oil solid or the tablets, injectables, and for the sake of discussion, today's discussion, we're talking about the active pharma ingredients or simply APIs. Okay. What's the API? If you look at any tablets that you consume when you are sick, we're talking about a very tiny portion of that, I would say, pill, which is called the API. It's in milligrams. However, it's the one that gives the therapeutic effect to the medications. The rest of the pill is outer layer and excipient. And when I said a chemical engineering degree or chemistry degree is good for industry because it follows the very same chemical processes of a unit operations, reactor, granulation, and also taking it all the way to finished products. However, the only difference between the petrochemical processes and the pharmaceutical processes is getting a GMP certified. It has to go through certain stringent process in order to produce a GMP, or what do you call it, the good manufacturing practice certified plants. Okay. Of course, there are so many challenges in the pharmaceutical segment, similar to any other segment that, industry has. One of the, I would say, one of the disasters or let's say main struggles that went through the whole world is, of course, COVID-19. COVID-19 reveals that there is a must, I would say a must, to have a national resilience of basic pharmaceutical needs. Now, looking at the right side of the slide, it's the production or producing countries of the active pharma ingredients versus the demand. And as we all probably would anticipate that almost 70% of this production goes to India and China for a variety of reasons. And the demand on the left side is different, you know, where the world uses the APIs in order to make medication, it's different from the right side. Now, after COVID-19, of course, there has been a wake-up call to all countries. And it manifested very clearly that regardless of the cost, it's very important and essential to have your own pharmaceutical value chain, starting from basic chemicals all the way to active pharma ingredients. I always give the analogy of this desalination industry and I would say power generation industry in the country. It has to be incentivized. There has to be collaborative effort between the academia, industry, as well as the private sector in order to bring up this industry to, I would say, to the surface. Okay. Saudi Arabia, as I would say, a country with a long legacy in petrochemical processes, definitely we still have a legacy in order to be a world leader at the active pharma ingredients. And one of them, obviously, is the perfect location in the Middle East, where there is a huge potential to be an export-oriented industry. If you recall the previous slide that I showed, out of $13 billion, the active pharma ingredients market is almost like 0.4. It's tiny. But without this active pharma ingredient segment, you cannot produce any conventional medication. It's like the fuel for the car. If you don't have a fuel, then you cannot have a car. And the target is not to just, have the industry for local consumption, because it will not be feasible. Always, day in, day out, we always, meet investors that would like to produce for a local captive use. That doesn't work. And it's very similar to the petrochemical processes. More than 70% of KSA production goes to export to the east and the west. And if you notice, like small countries like Ireland, a small population, I don't know what is it in Arabic, but it's a tiny country with a 5 million population, but they have an export worth of $50 billion to the east and to the west. Same thing goes to Singapore. They have an active export, but almost $70 billion to the whole North and South Africa. And I believe and I trust that we have the very same capabilities to have an export-oriented pharma industry and specifically the active pharma ingredients. Okay, fantastic. Definitely, we have a legacy, as I mentioned in the beginning, of oil and gas, and it's a huge sector. Whether we like it or not, it's still the biggest sector in KSA. And we can build on that legacy because I believe the talents that are running the pharmaceutical, they are mostly engineers, especially when it comes to operation. Knowledge of basic, I would say, chemical or oil industry would give you the capabilities to produce any pharmaceutical ingredients. All you need is a simple certification in GMP and other stringent regulation. Otherwise, I think we are ready. We always hear from investors that we don't have the right talents, and I would argue that no, we have very bright talents. To have seen today is impressive from the ladies and boys outside this exhibition. It's impressive, the talents that they have, and also what I've seen in the poster today. And I told them, I had a chit-chat with them, and I told them that, please, what you are doing is excellent, but at the end it has to resolve an industrial issue. You cannot have just a paper and you file a patent, but it doesn't have industrial application. So it's very important to link the industry to the academia, because at the end, if you don't have an R&D, sound R&D system, then you cannot have any medication or especially a niche industry like pharmaceutical segment. Okay, excellent. Now looking at the basic value chain of an active pharma ingredients, looking at the bottom there, because I know that we have Aramco and SABIC, so we'd like to please them. So we have a huge building blocks of petrochemical streams from SABIC and Aramco. And when I mention SABIC and Aramco, it means they're affiliates. We have, mashallah, a state-of-the-art plants scattered all the way in the east, in the west, also in the south. But at the end, they produce what you call it the building blocks or the basic chemical streams. However, those has to be taken further to produce more downstream, or what you call it the fine chemicals, all the way to the active pharma ingredients. So starting at the top, we have a very solid industry, SABIC and Aramco, and we have a very big missing piece of basic intermediates or advanced intermediates leading to the pharma ingredients. And luckily, we have an active pharma ingredients in Riyadh called CAD, which is part of SPMACO. Now, going down in order to also produce excipients, we don't have that capabilities. We have the right side, we have the left side of the equation, but we don't have a right side. Although if you look at far right in terms of formulation plants, we have more than 57 plants, whether they are doing secondary packaging or a primary or even from formulation. So we know the issue, and we'd like to resolve it with private as well as also the academia. Because the knowledge that I mentioned, going from basic chemicals all the way to active ingredients, it's easily said than done, because at the end you need a bright synthetic chemist, a bright synthetic chemical engineer to take it all the way. I would say, if someone asks me, is it possible? Yes, of course it's possible. Is it easy? No. Because you have also to keep in mind that there are major players who have filed patents. So in order to take it from the left to the right, you have to know exactly what you are doing, and you have to be clever enough not to infringe any IP at the end. And you have to make it commercially viable. And that's the beauty of having KFUPM here in place, because I know that you have the chemist, you have the chemical engineer, as well as any other engineering disciplines that can support us to take it all the way, from basics, all the way to fine chemicals, all the way to active ingredients. And that will be available after the session, so we can have a discussion if anyone can, I would say, willing to collaborate with the Minister of Industry in order to have this happen. That would be great, really win-win deal for the academia and the industry as well. Okay, fantastic. And zooming into more, I would say, value chain of pharmaceutical all the way going to active ingredients, we start to see, in order to be fair with other, I would say, petrochemical companies, we're starting to see smaller companies versus Aramco and SABIC affiliates like Imanol, Sibchem, GDI, who started to tap into this business. However, we need more into those companies who can work with Aramco and the upstream producer to bring those fine chemicals all the way to the active ingredients. Very important. And also, honestly, if you talk to SABIC and Aramco, which we have done in the past, they have, I would say, a borderline where their responsibility or their mandate ends at the basic industries. They cannot go down all the way to active ingredients or even to the intermediates. And when we talk to the right side players of pharmaceutical companies and active pharma ingredients producers, they cannot go upstream. So we still have this piece that we need to fill out. Okay, fantastic. So this is the work that we have been doing after COVID, because, it's a wake-up call not only for Saudi Arabia, but for the whole countries. So what we have identified out of almost 9,000 products registered at the Saudi Food and Drug Authority, SFDA, we have narrowed that to almost 900 molecules. And surprisingly, what we have found after COVID-19 and doing our detailed analysis, that each government entity, they have their own priority list of medications. The SFD has their own list from their perspective. Same thing goes to the Ministry of Health, Ministry of Economic and Planning. So what we have done, we derived a priority of the priority list, and we came up with almost 200 molecules, small and large, and eventually we ended up with 140 APIs of interest to the country. And it's no secret, we have posted that long list of priority molecules at the local content and government procurement agency called LCGPA for any interested investor, whether it's, I would say, private, small, or even large investor. And they will be giving special incentive in order to make this business case lucrative for them as well. So if you go over to, if you browse the link to the local content, you will find those priority molecules. And also you'll find a form there where you can fill. And after that, there will be definitely a dialogue with the local content and also other government agencies in order to probably take a deep dive on which incentive you'd like to have, and also what's your localization plan of that active ingredients or even pharmaceuticals. Okay, what's the value proposition? We always also get this question day in, day out. Why Saudi Arabia? Why not somewhere else? Because if you have an investor, definitely they will not only look for Saudi Arabia, but they will shop around. They will go to the countries in the Middle East without mentioning names, and they will compare it to the incentives that we have. I was talking before the session with Dr. Ba'aqil, and he asked me, why don't we have a pharma industry, I would say a rigid pharma industry yet? And I told him, because we are giving more incentives. So over-giving incentives is like under-giving incentives. So the incentives, they are huge for the pharmaceutical industry, and that would put some reluctance on the investor to go down, I would say, the value chain in order to produce the real pharmaceutical product, rather than having only tapping into the secondary packaging of the pharmaceutical industry. So just to give, I would say, high-level incentives that we have in the country as a whole, alhamdulillah, we have a political stable country compared to any other countries in the region. Also, we have pretty competitive utility power and also land cost versus other countries. We have also have strong, I would say, IP protection in case A. We also get inquiries from investors that is the IP protected? Simple answer is yes. As also an example, the JVs that we have with SABIC and Aramco, we have JVs for almost 50 years so far without major infringement cases. Same thing, we have, I would say, 35 industrial cities located at Mudun, and also major industrial cities located in Jibel and Yanbu. And also, we have a huge portfolio of chemical streams that need to be examined, and I'm very sure that we will find plenty of those chemical streams that can go into pharmaceutical industry. We have also financial incentives that I'll show in a minute. We have, of course, the local content and government procurement agency incentives. They can give you up to 30% price preference for your locally produced product. For example, if there is a product that costs $10 and the local product is $13, they'll go and buy the local product of $13 because there is a 30% price preference. We have, now we're talking about the affiliate or sister organization that we have within the Ministry of Industry ecosystem. One of them is called the Saudi Export Authority, where they take you up to exhibitions, global or local exhibition, or even regional exhibition, in order to participate and show your products free of charge. Also, we have, as we all know, that we have 5 major industrial cities, and also we have what you call it the Saudi Exim Bank, the Export and Import Bank, where they give you your money up front in order to be able to export, especially to least stable countries. The National Industrial Center, where I come from, they provide the know-how, they provide technical data free of charge to any investor. And also we support with feasibility study and any other data free of charge. And of course we have the Saudi Industrial Development Fund, where they can provide up to 75% of the loan with a long grace period of 20 years. So I think we have a lot of incentives. And this is, those are the incentive back outside the Ministry of Industry boundary. We have definitely the SFDA. So SFDA recently got a maturity level 4, meaning if you have a certified product, pharmaceutical product or medical devices that's certified here in case A, you can easily manufacture it locally and export to the whole world, not only to the Middle East. You have also the Ministry of Investment, where you can have your own investment, 100% ownership without restriction on cash in or cash out. And last but not least is the local content, where they buy through government, I would say, arms, buy in bulk quantities, and they give you offtake for 2+1, almost 3 years. And of course, we have the price incentives for local product, and also we have a mandatory list, meaning that if you have a local plant, and this plant is able to produce for local market, then the government will buy from local market. With this, I conclude my slide. I hope that you enjoyed it. Try to make it short and sweet. I know that, it's almost evening time. So thank you so much. Great to be back again to KFBM. Thank you so much. Appreciate your time and listening to my presentation.
Thank you very much, Mr. Abdullah Al-Ali, for that insightful and inspiring presentation. Once again, I would kindly ask Dr. Ba'aqil to present a token of appreciation. Now, ladies and gentlemen, we move to our final keynote speaker, a remarkable business and innovation leader who has made a lasting impact across industries. Mr. Sami Al-Safran, Group CEO of Innovest, is a leading figure in the paper manufacturing industry. He pioneered vertical integration and sustainable production practices, transforming MEPCO into the region's foremost vertically integrated paper manufacturer and the largest exporter in the MENA region. He served as Group President and CEO of the Middle East Paper Co. from 2004 till 2024 and now leads Innovest, which is a Saudi Arabia-based real estate investment and development company specializing in residential communities and villas. In addition to his executive role, Mr. Al-Safran also serves as Vice President of Manafa Featured Trading Company and the Chairman of the Arab Federation for Paper, Printing, Packaging Industries. In recognition of his outstanding leadership, he received the CEO of the Year Award 2024 at the Middle East Enterprise AI and Analytics Summit. Please join me in giving your full attention as we welcome Mr. Sami Al-Safran to deliver his keynote address.
Assalamu alaikum wa rahmatullah. Thank you very much for giving me time. I know it is getting closer to the end of the day. We'll try to make it interesting because the topic we are going to talk about it right now is probably something that touches our daily concerns, and we speak about it in a fragmented way. So here we are going to club actually the three things, which is the policy, the infrastructure, and the public engagement for a very concerning subject, which is the waste management here. Just to start with, I would like to introduce my company, which is MAF, and here we are actually delivering an environmental solution and a circular economy for waste management. We do different things between collection, transportation, and recycling. We have different facilities, one of them in the south for plastic recycling, the other in the west for waste paper collections, and now we are starting our facility in the eastern region for waste management. We'll jump immediately to the second concern part, which is what is happening in Saudi Arabia right now. Saudi Arabia in 2015, they have announced their vision to achieve the landfill diversion of the landfill by almost 90% from the existing situations, which is probably this one is equivalent to what is happening in the most of the modern world. And in particular, we are focusing here into the municipality waste, the hazardous waste, the construction demolishing waste. Now, in some of the sectors are a bit mature due to the fact that it's a concern, like for example the hazardous waste. So we'll find some initiatives are going on there, but other sectors are still in a very basic level. If you compare the situation right now, we are talking about an existing landfill diversion does not exceed more than 5-10%, and this is a very low figure. If we see the situations in North Europe, we are talking about almost 82%, like the case in Germany. And as usual, the Saudis are starting late and they want to be pioneer, and this is what we are working with right now. What does that tell us? It will unlock actually an investment opportunities up to 500 billion. It will create jobs up more than less than 100,000 and in contribution GBD of 750. Now, in particular, let's classify the waste we are talking about here. Here we are talking about The most concerning part is the municipality one, which we see and we are interacting every day. Now, regarding the volume figures, we do not have really a specific volumes until now because the quantities are changing. Like, for example, in the case of the construction demolishing waste, you will find when there is a heavy construction is going on, the numbers are shooting up very high. It's the other way around. When things get slow, then the numbers slow. So until now, we do not have an absolute figure. So here, I would say that this is a close estimation from our side about what we see from collecting the data, the tendering situation is going on, and some of our assessment comparing with what's happening right now. No doubt the major contribution, three part of it, is the municipal waste, the industrial waste, and the construction demolishing waste, which is a concern right now. Now, moving forward with the subject, okay, what is needed to be achieved to reach up to that situation, moving from 10% all the way to 80%. Definitely, there is an importance of developing an infrastructure. There is an importance of a public engagements, and finally, also there is an investment that is required in addition to the regulating that had been set up here. Now, let's take the three dimensions one by one. If we speak about the policy and regulations, in 2015, the Ministry of Environment have established the National Waste Center shorted by MOAN. And in the first 5 years of it, they have launched the policy and procedures of MOAN. They have identified the EPR scheme. They have set the regulations for the system. And also, we could see some ground activities are going on in terms of monitoring and control and digitalizations and things like that. So we believe this one is actually helping building the ecosystem of the investment of on the waste management side. Now, needless to mention that the waste management transformation process is not actually a one-day journey. I mean, we have mentioned some interesting examples, like, for example, North Europe, but it's something we need to know that it took almost like 50 years to reach up to those figures. Now, here, the challenging part for us is that we would like to achieve this one in less than 20 years. And that will require definitely different things. One of them is the setting of the management, and the other one actually is the building the infrastructure. Now, to reach up to that target, if you had a chance to see the master strategic plan that have been developed, it will require an investment up to 500 billion, which is until now we are investing less than probably 50 billion in that sector. The second thing is building 25 different facilities to receive the materials, okay? In addition to another 900 treatment facilities will be cascaded where. Look, it's important to highlight something. Now, let's take, for example, the municipality waste. The municipality waste treatment alone will require more than 10 different streams for treatment, because the outcome of the municipality waste is that definitely part of it is the recyclables, like, for example, a paper, plastic, and a metal, and every one of them will require actually a processing side. Then after that, you need to produce the organic side of it, which most likely you could do it through digestions and producing methane gas for biofuel, or building the composting side for soil treatment. And then finally, what is left not to be treated, it has to go for what's called an RDF, which is the refuse derivative fuel. And we could see some initiatives has happened here. Like, for example, I could recall 2 sites available right now. One of them is in Jeddah Cement Safwa, and the other one is in Medina Cement, which is a piloting are going on there. Now, moving forward with the last one, which is the public engagement, and this is really a very concerning issue, because when you sit with everyone and talk to him about waste management, they are very excited, they like to speak about it, they like to hear about it, but the human behavior remains the same. And we could see, like, when we run the trials and we start to establish 3 bins concepts in any places, you will always find the amount of mix reaches more than 50%. So it is really getting really challenging. Now, the interesting part, although we have done this one through the young youth, and we start to give courses for that one, but because the whole ecosystem is not available to do so, that's why we always lose the directions. Now, why we are still doing it? Yes, we are doing it because we have to build and engrave in the concept that starting the landfill diversion start from a proper segregation from the sources. Now, a few initiatives have been successfully made, which is most likely, which is related to the charity part. So if there is, for example, any program have launched by the charities, successfully we achieve the result. I remember 3 years ago with the King Abdulaziz University, we have launched a program called Mawakib al Khair, and that one is to collect the old books schools after that one to serve the nearby mosques. And luckily, the successful was 80%. So those are one of the drivers. Actually, is the spiritual engagements for the responsibilities. But we believe, finally, as a rule of thumb, without a financial incentives, there will be no reason to segregate. And this is why, if you see the policy and procedure for Mawan, they have stated what is called EPR, and the EPR is the extended producer responsibility. Now, the challenging part is that when you buy a bottle of water and you consume it, the easy one is to throw it. Now, what is the right thing to do is that, number one, do not buy the water, okay? Use actually, we call it recycled bottles, or use actually glass water and things like that one, which eliminate generating the waste. Now, the second thing, when you bought the bottle, and this is actually the EPR schemes, you have to pay an extra additions, which is 5% or 10% of the cost, and that's the cost of the treatment. Because if we decided to reach up to that kind of a diversion, let's say, for example, for the case of municipality waste, then you will need an incineration. Now, if you look at the financial model for the incineration, 60% of the revenue is coming from the gate fees, what's called. And that gate fees, and this is the untold story, that if we see in, for example, the case of Switzerland, to receive the material for incineration and generating energy, they charge actually more than $150 for that one. And that actually what incentivizes the operation, because the cost of operation of incinerations is very high, and the sales of the electricity is not enough to cover the cost of the energy, because usually the electricity contributes with 25 to 30% of the revenue. But the 60% revenue should come actually from the gate fees, which is produced by the EPR scheme. And technically, this is what we should see going forward with that one. Now, have we seen some initiatives? Yes. Let's say, for example, in the case of UAE, anyone who has visited UAE lately, he will find that every time you buy from the grocery, you pay for the cost of the bags, similar to what is happening in Europe. And this is why the Emiratis, they choose actually to start from the end by building incineration there, and all the material that comes for incineration, and those charges goes actually to feed the scheme of the operation. And that could be enabled. I think in the case of Saudi Arabia, due to the geographic spot, due to the environmental concern we have, because incineration is not a solution, still it will contribute to the carbon footprint, and this is something we would like to avoid it. So the strategy here is that we would like to maximize the recycling and diversion from the production. And that's why we started with the layer of monitoring. We started with a digital platform. Now, I think in every municipality, you will find a platform called Manassati in addition to Mawan. And both of them actually is generating a manifest to track the waste materials from the source to the end to the recycling. Now, moving forward with the subject, and probably I jump immediately to speak about the achievements here and what has been done between building the framework, between the EPR scheme, okay? Now, going forward, what we are going to see, we will see some enhancements is going to be there. We are going to see, for example, the digital platform will start to gradually monitor the detail, because until now, the digital platform is monitoring the municipal waste, is monitoring the industrial waste, okay, in a smaller scale, but doesn't cover to the whole horizon. Now, why I'm saying this one, okay, because let's take, for example, the industrial hazardous waste. It's one of the topics we are monitoring right now. And we could see that by the way, it's a concern magnitude. It's 7 million. And the 7 million is that what has been reported. And we know we are actually declassifying the volumes of the hazardous waste that could not be treated, because some of the generated waste, I mean, whatever we call it waste, because it doesn't match to the nature of the earth. So that we call it NER. So in any industrial process, and especially the mining, once you change the nature of the material, then it becomes a waste that you have to convert it to natural back again. Now, some of those treatment technology are yet not available to treat, to bring back to the normal. So if we declassify this one, still we find another 7 million are available. It will require actually a massive investments. For example, we are aware, for example, for the water oil contaminated water, it's easy to treat, it's easy to handle. But when you come to the case of spent caustic, then it becomes really a challenging situation. Now, needless to mention that some of the actually hazardous treatment that we have does not have actually the infrastructure for treatment. And still, some of the material, we are actually exporting them outside Saudi Arabia for specialized facilities to conduct the right treatment. Now, we believe going forward, we are going to see some infrastructure has been built. We are going to see some more facilities is coming to the treatment. And hopefully by the 2040, we could reach to the target of the landfill diversion up to 90%, which actually guarantees a sustainability of the earth for our generation and enhance a circular economy for more than 750 billion riyal. By this, I conclude my presentation, and you are most welcome for any question. Thank you.
Thank you very much, Dr. Mr. Sami Al-Safran. And I kindly request Dr. Baaqil to the trophy. Ladies and gentlemen, this concludes our keynote session. We'll now take a coffee break. Please enjoy some refreshments and networking. We'll resume in 30 minutes with our parallel sessions. Thank you.
Assalamu alaikum. Good afternoon, everyone, and welcome to afternoon session. My name is Professor Bassam Al-Ali from Chemistry Department. It's my great pleasure to introduce Dr. Florian Stadler. He has doctorate in engineering from Friedrich Alexander University Erlangen-Nuremberg, Germany, in 2007. From 2009 to 2014, he was professor at Chanbuk National University in South Korea. And from 2014 to 2024, he was distinguished professor at Shenzhen University, China. He is working on rheology and with a focus on structure property relationships in various systems, ranging from polyolefin to ionomers to hydrogels and supramolecular assemblies, as well as special nanoparticles for adsorption, gas sensing, and photocatalysis. He has large number of publications, around more than 350 in peer-reviewed. Doctor, he is now at Chemical Engineering Department, leading interdisciplinary projects, supervising graduate students, collaborate internationally to advance the frontier of chemicals and materials engineering. Okay, join me to welcome Dr. Florian Stadler to the podium.
So, thank you very much. Oops. The presentation basically is something that started during Corona summer 2020, when, well, as some of you might know, in China we were not allowed to travel. Just before the summer, my very much esteemed colleague Zhu Guangming came to my office and asked me for help because he has faced some problems about understanding what happens in a material class that he's developing, which is Pickering emulsion. So in short, what is a Pickering emulsion? A normal emulsion means you have two liquid phases, usually oil and water. And a Pickering emulsion means you have solid particles at the interface. And we are going to discuss what kind of influence that has if you use different types of particles on the interface. So here's some funding that I got for this research, and the starting point is 3D printing of emulsions to basically get a skeleton of particles residing at the interface that you get as a super soft, super light solid when you simply remove both the oil and the water from it. So it means you 3D print an emulsion, and then you remove the oil and the water, and you get a very porous, very light structure, and that can be used for various applications. And he did that with graphene oxide, so that was the starting point. So, because of the Corona summer, as I said, I had a lot of time. I couldn't go to my summer holiday, so I spent all the summer going through the literature, which was about 1,100 papers at that time, and found out, okay, well, there's some literature, but nothing that really makes me so much happy. So I started thinking about how to do it better. So what do we have as a sample? We have Pickering emulsions, an oil to water ratio of 1 to 2. That means we have oil droplets in water. The oil phase is paraffin oil. And we have DDAP. The chemical formula is shown here. as a co-emulsifier, which is still necessary to form the emulsion properly. And we use 3 different Pickering emulsifiers and compare them for their behavior. So graphene oxide, cellulose nanofibers, and MXene, which is a sheet-like hard material. And we're going to have a look at that in different rheological protocols. Besides that, we're also doing microscopy, optical and electron microscopy, and we're doing normal rheology. That means viscosity functions, but unlike usually you don't start only from one direction. You start first going up in shear rate, then down, going up and going down again. Because here we have a dispersed system, we need to erase the previous history. So the first step that we find is usually quite different, but the rest is like that. Then we're doing strain sweeps, which means we increase and decrease the strain to maximum 100, 300, and 1000%. In general, if we go higher than 1000%, the sample will be completely destroyed, and so it is not advisable to go much higher than that. And we check the frequency dependence at 5 different deformations as well as we do MITT. So probably you never heard the abbreviation MITT, and that is quite logical because that was a protocol that we invented for this research. And so I'm going to start with explaining what it is. So the start is that we use a classical sixotropic loop test, which means classically we apply a deformation and we see how that changes the structure. So the 3ITT, which is the 3-interval sixotropic test, means we oscillate the sample a little bit, see what properties it has. Then we make a startup flow, means we shear. How much? Depends. And then we do another experiment and see how much that has changed the properties. MITT does something similar, but in a more systematic fashion. That means we basically have a loop of a startup flow and a time sweep, means an oscillatory test, 2 minutes shear, 5 minutes testing what kind of properties it has, including, of course, recovery time, and we go from 1, 3, 10, 30, 100, 300, 1000 reciprocal seconds, and then back again. So you can imagine it's like this. We hit the sample a little bit, measure what it does. We hit it stronger, measure what it does, hit it extremely strong, see what that does, and then do the same thing backwards and see what kind of effects that has. That can be, that's a protocol which approximately takes 2.5 hours. And in order to evaluate that, because you will get maybe something like 3,000 data points, I developed a MATLAB script to evaluate that in an automated fashion because nobody wants to go through that much data. So how does it look like? You can see here the shear rates, how we go up, down, and these are the viscosities that we are measuring. Pretty obviously, we have a shear thinning liquid. If we go up in shear rate, we go down in viscosity. That is logical. When we repeat exactly the same time sweep afterwards, that means we oscillate always at 1 radian per second and 1% deformation, which is really very little. You can see the moduli here. And the result, and that was something that really surprised me myself, was that if you hit the sample hard, it becomes stronger. And you can see from this example, becomes stronger by approximately factor 6. And then when you shear slowly, it goes back to its original properties again. And that was even more surprising. So, based on that, we said, okay, well, we need to look at that a little bit. So the protocol, the evaluation then is, we simply extrapolate the final value for storage modulus G prime, for loss modulus G double prime, and for the 10 delta. You can see we go up like this, we come down like this. The values are pretty much the same for all three quantities. So we can clearly see we make the emulsion harder when we shear the hell out of it. So that, of course, leads to the next question, which is pretty obvious. What happens when you change something about the composition? And so we changed from graphene oxide to cellulose nanofibers. And you can see we make the emulsion softer if we shear the hell out of it, and then it goes halfway back. So it means, okay, that makes more sense. But ultimately, it raises the interesting question. Why do we have two types of emulsifiers, one relatively flexible plate or sheet-like material, one relatively flexible nanofiber? Why does that make so much of a difference? That is the question. And so this is a systematic study, here normalized to the viscosity at 1,000 reciprocal seconds and to the modulus after 1,000 reciprocal seconds. And you can see the viscosity functions for different contents of these nanofillers, they look relatively similar. So that doesn't tell us too much. But you can clearly see the GO, these are the black samples. They lead to lower values, which means the sample gets stronger when you shear it. On the contrary, when you have the cellulose nanofiber samples, then, well, not much change happens. And when you have MaxScene, then you find an interesting behavior. For low MaxScene contents, you destructure the sample completely. And for high, that means you destroy the sample, and then it's much softer after high shear. For high contents, you have the opposite effect. So, let's see what that means when we look at it through other ways. So here we have a startup flow, and you can see here the normal force, the force how much the geometry pulls the sample together or pushes it apart, is negative, which means the sample pulls the geometries together at high shear rate, while if we have cellulose nanofibers, when we have different contents, that behavior changes. So we can say, okay, if we have a little bit of graphene oxide, then we get a negative value. If we have a lot, then we have a positive value. So that, again, is something which is difficult to explain. So, simple explanation. If we stretch our droplets, that leads to a contraction, and that leads to a negative normal force. Of course, the stretch mainly happens at a high shear rate. If we have a lot of material in it, then the interfaces get stronger, and then the particles start bumping into each other, and that leads to this kind of upturn. And this is what we find at higher contents. So when we compare the different startup flows for the GO emulsions, you can see, okay, the MITT results, which we of course also have, and the viscosity functions agree very, very well. We don't see much of an effect. However, if we look for the cellulose nanofiber emulsions, we can find, there's some kind of bump, which means there something happens, and that is that the droplets are colliding to each other. And you can also see here we don't have an agreement anymore. So, when we then look at the MaxScene emulsions, we find it suddenly becomes unstable. So there's some kind of intermittent oscillation behavior, which means the flow becomes unstable. And this kind of behavior is something which is called Rio chaos, and that is very, very poorly understood so far, so I'm not going into detail too much anymore. The really interesting thing is also when you look at the nonlinearity limit. So you can see here we have G prime and G double prime, and we just at one frequency, and we increase the deformation. And we can just look at when do we see a dependence of, G prime and G double prime on the deformation, marked by this red line, or this vertical line. And you can clearly see for cellulose nanofibers, this non-linearity limit is at around, let's say, 7%. If we look at the graphene oxide, then we are at 0.05%, so much lower. MaxScene is somewhere in between. So how do we understand that? The non-cellulose is halfway water-soluble, so it's somewhat flexible and it's fiber-like. That's why it doesn't distort the normal non-linearity limit that much, which is around 30% for most polymers. Graphene oxide is a sheet-like material which is pretty long, and that disturbs this kind of thing very much, and we know that for materials which have a lot of fillers in that, the nonlinearity limit is very low because of some kind of effects between the interfaces. And graphene oxide is a little bit less effective at that, so it's somewhere in between. Good, so I'll skip that part and go to conclusions. So, in conclusion, we can create Pickering emul gels, that means emulsions with gel-like properties, that can be based on different emulsifiers. We can distinguish those by various tests, especially that MITT test, while the viscosity functions remain relatively similar, but again, the normal forces show clear differences, as well as the linear viscoelastic limit shows a difference depending on filler shape and flexibility. And with this, I thank you for your attention.
I think we might have just time for one question, if anyone would like to ask. Okay, thank you, Dr. Fleurant, for interesting talk. It's my great pleasure again to welcome Dr. Anton Nagy. Dr. Anton Nagy is originally from Chicagoland area. He is a chemical engineer turned entrepreneur based in Germany. Best known as the founder and chief executive officers of ELS, Integrated Lab Solutions in Berlin. He did his BS at the IIT in Chicago and MS in chemical engineering at Worcester Polytechnical Institute, where he had his first exposure to catalysis, doing acrolein catalysis synthesis and testing in the group of Professor William Moser. Then he moved on to work as intern in the Shell laboratories in Amsterdam and subsequently did his PhD work in heterogeneous catalysis at Max Planck Institute in Berlin in the late 90s. Okay? Dr. Anthony is presently visiting KFPM, of course, based on the mutual projects. He is well known in highly automated R&D pilot units and that serve chemicals, petrochemicals, and pharmaceuticals. Please join me to welcome Dr. Anton Nagy to this session.
Thank you very much. Can you all hear me? Oh, I think it's working, yes? Okay. Thank you for that introduction. Salam alaikum, good afternoon. The last talk I gave at this university was, I think, about 15 years ago at a joint Japanese KFUPM conference. So I was patient, and it's really a pleasure that the patience paid off. And I'm also having the pleasure of working with Dr. Atiani, who I've known for many years, and we're now doing a plastics recycling project together. You're going to get a bit of presentation whiplash today because we're going from a very scientific presentation to more the world of a small startup in Berlin. I want to show you a couple of examples how we've addressed circular economy applications with unique pilot and laboratory scale equipment, and a unique approach that we're taking now, which supports our clients by making it possible for them to operate units much more quickly than they normally can. So I'll get started in the hope of staying on time. ILS is a company now with approximately 65 people working there. I founded it in 2000. You see here we're based in Europe's largest science park. It's called Adlershof. This is our workshop. You'll see here a variety of units. This is a reverse water gas shift unit with a combined methanol synthesis. So it's basically a whole plant in a single unit. At any given time, we're typically doing 6 to 10 units in parallel in the workshop in Berlin. This is our laboratory, which I'll be talking a lot about today. That's an ammonia cracking unit. Here we can actually operate our units with real chemistry. And that's one of the focuses of the talk I'll be giving today. In Germany, if you don't have a kicker game, it's hard to keep people working efficiently, so that's important. And this basically gives you an overview of the entire shop. So 500 meter plus 200 square meter workshop, so 2 workshops plus a laboratory. We're fully privately funded, so we don't have any VC companies that own us. We bootstrapped the company over 20 years. I will basically explain today the what we call the chemical commissioning values proposal. This is where we test our units with chemistry before we deliver them to clients. And I'll give you 3 examples of where we've applied that. The first one is going to be high throughput ammonia cracking. The second will be plastics recycling. And the third one is a green hydrogen application that we did, which eventually helped us start up in Berlin. So what is this proposal I'm talking about? Basically what we find is, when working with clients around the world, the more complicated a unit gets, the more time we actually often need to get the unit working on site. If it's a simple unit, typically you can get it done quickly. And doing an FAT, a factory acceptance test with water and nitrogen, that's always easy. But what's difficult is once the unit gets on your site and you're doing real chemistry with it, you get corrosion problems, blocking problems, cold spots, whatever. Chemistry can be very unpredictable regardless of how much engineering you do. And what we find is we came up with a package where we said, well, let's set up a laboratory where we run your unit with chemistry, confirm on our site that it works 100% to your satisfaction before we send it off. Well, that means we had to build up a laboratory in Berlin, which is what we did. And to basically give you kind of a comparison, the red bars here show how things used to work. So no chemical commissioning. And what you find is you order a unit and the cost to the client is basically what you ordered. You have some travel costs associated with coming out for the factory acceptance test. Then we have the SAT. Here you're starting to, your operating expenditures, your CapEx are starting to increase because we're on your site. We're using up your time. If all goes well, we're done at the SAT, but as often happens with highly custom units, especially for challenging chemistry, you end up with debugging problems. And this is just an example. If you have 1 month or 3 months of debugging, the cost of you running it on your site, you doing the debugging, they can really become quite substantial, especially in comparison with the original price of the unit. And this is the reason why we ultimately decided to go this route and also to offer a service package which not everybody can provide on the market. So I'll give you 3 examples of where we applied this, and all 3 of these are for really novel circularity applications. The first one is going to be high pressure ammonia cracking. So basically we were approached by a client. They want to store green hydrogen. That's a big topic, particularly in Germany right now. So how do you get green hydrogen from Australia to Germany or from South America to Germany? Well, liquid organic hydrogen carriers, LOHCs, are one route. Another route, which is becoming very popular right now, is converting hydrogen to ammonia and then cracking that ammonia after transporting it. Ammonia is a liquid gas, which is a liquid at fairly low pressure and can be much more easily transported than hydrogen. This client basically had a number of issues that they wanted us to address. Water is a common contaminant in ammonia, and it's a poison for ammonia cracking catalysts. So we have to remove that water, but also be able to add it later in a controlled way to do poisoning studies. We also had to show that these reactors have no blank activity at 800 degrees. So running ammonia in metal tubes at 800 degrees, there's not a lot of literature on it. I'll show you how we address that. We want to operate in a kinetically controlled regime, no mass transfer, and at up to 50 bars. That 50 bars is important purely for economic reasons, because that way they can produce hydrogen at high pressure already. So I won't have time to go to everything in detail, but to give you one example here, this is a typical example of a ammonia cracking catalyst and what happens if you add even minor amounts of water. So you see here, this is an example of a barium cobalt versus a barium iron catalyst. This is the source, and here you see they really get, with this barium iron, an 80% drop in conversion from minor amounts of water. So how do we address this? Because water is always present in ammonia if you get it from Linde or Air Liquide or any supplier. Well, what we did here is we basically incorporated in situ adsorbers. These are absorption columns where there's a adsorbent which selectively absorbs the water as steam at very low concentrations before the ammonia enters the reactor, and that way we know we're only getting high purity ammonia entering the reactor. So our baseline is no water. Then we needed to figure out a way to selectively add very, very small amounts of water. So if you look at here, we're looking at 50 to 500 milligrams an hour. You know, that's less than a drop of water that you're putting in an hour. And for that, we worked with extremely low dead volume capillaries here. So very, very small tubing. Anybody from a big plant would probably laugh if they saw this. And to be able to do this in a pulsation-free way, we need to get this water in, but also vaporize it continuously. We work with a system where this pipe sticks into a hydroscopic ceramic wick, and via the capillary forces of that wick, it draws the water out into the warm zone of the reactor, where it's then continuously vaporized. So it gives you nice pulsation-free vaporization. And we demonstrated that unit on our site and how it worked. This shows you how we work with a quartz tube in metal reactor construction. That's how we were able to address the materials issue, because at 800 degrees, a nickel-containing high-temperature alloy is always going to be active for reaction. But by putting this quartz tube liner inside the reactor, we were able to make sure that they get zero blank activity, and it ensures longer lifetime of a reactor. That's one example. We operated it for 2 months. We demonstrated it has long-term reliable ammonia dosing. We had to fine-tune the catalyst dosing procedures for that. Believe it or not, in this long reactor, the catalyst bed is only 1 centimeter long. Most of the bed is just for preheating the gas, because we're operating at very high space velocities, because we want to operate under differential conversions where we know we're not mass transfer limited. We were able to demonstrate the pulsation-free water vaporization, and we were able to do kinetic studies for the client in the beginning. A second example is chemical recycling. So here we were approached by the company Norner. Norner is a company here based in Norway. So Norner is not a polymer manufacturer. Norner is a company which typically converts polymer beads to bottles. So they blow it, they make the final product out of it. But they were interested in getting into the plastic recycling business. So they approached us with the challenge of how can we convert mixed plastic waste to fuels, primarily because in Norway they have a big shipping industry and they want to be able to operate ships in their in Norway in a more circular way. So what we started with them is we had to do a lot of testing up front. So we had no idea how these materials would behave. So this is an example of one of a variety of reactors we tested. This was, for example, a vertically stirred fluidized bed reactor. So you have a stir and a fluidized bed reactor. This is working with a BASF FCC catalyst. And we did a lot of cold mock-up testing here to make sure that we got the reaction, the reactor dimensions and the hydrodynamic conditions of the reactor optimized to really be here in this sweet spot here where we have a good ebulliting bed. That's what we're shooting for. We don't want any bulk mass transfer of catalyst out of the reactor. And we did a lot of testing as well, looking at various PP, PE mixtures. That was challenging because if you work in the wrong temperature window, you start to get cross-linking of your polymer. The viscosities go through the roof and it starts to block. Looked at a bunch of different geometries for how can we prevent the catalyst from dropping down into our feed pipes and ensure that we get a really good homogeneous ebulliting bed. So all of these tests were done in this chemical validation laboratory and ultimately culminated in this unit here. So what you'll see in this unit here is you've got a plastics feed hopper here. This adds the shredded plastic waste. It's a mixed plastic waste, so PE, PP, small amounts of PVC can be contained. This is then fed here to a double screw extruder where it's melted, extruded into the reactor. So the extruder melts the feedstock and continuously feeds it into the fluidized bed reactor. This is the fluidized bed reactor. Here we have a recycle for the gas stream to keep the fluidized gas in place that we need to keep the bed fluidized without having to add nitrogen, so more accurately reproducing what you would have in a full-scale reactor. And the heavy fraction, in this case, a paraffinic fraction, so we're targeting paraffin, naphtha, and kerosene fractions. The heavy paraffin fraction can be recycled back into the reactor for additional thermal cracking if they want to target lighter products. They were targeting primarily naphtha products in these studies. You have also the ability to add catalyst online. It has a full online and offline GC, so you can do online gas analysis, and after test you have a SIMDist in there which allows you to basically look at the rough product fractions that you're making. This is very similar to one of the units we're going to be providing KFUPM. Yours is actually a bit larger, it has more functionality, but that has been in operation now for almost 3 years on Norner's site in Norway. A lot of the problems we had to overcome in our laboratory are things like this. So FCC catalyst, we frankly underestimated. It's called fluid catalytic fluid catalytic catalyst. Fluidized catalyst, yeah, FCC, fluidized bed catalyst cracking. I'm getting through blah blah. It behaves very much like a liquid. I'm focusing on the F, the fluid part. And what we found is this FCC catalyst kept going back into our tubing, into our extruder. Extruders are not made to be married to pilot plants. This was quite unique for us. Also incorporating the process control system was quite challenging. They're not used to working with typical PCS systems that pilot plant manufacturers make like we do. And this is what you were typically getting. So if you get FCC catalyst combining with this PP-PE melt coming in, it immediately just forms a horrible goo, blocks up all of your feed lines. So it took quite some time to understand how we have to build the unit geometrically to avoid this happening. We also found that if you're doing fluidized bed pyrolysis, fast pyrolysis, you're rapidly quenching the product. You form very stable aerosols, and they're very hard to break. Those aerosols will end up in all of your downstream tubing. So we had to work with different column packings to avoid that from happening within our condensation columns. I mentioned before the cross-linking issues we had. Paraffin blockage was another issue, having to optimize heat tracing. We had to find a way to remove ash and fines. We do that with a combination of a very small cyclone, which we developed ourselves because you can't buy cyclones for units of this size, in combination with a special filtration system. And even one of the most basic things, the overall item enclosure it was in got so warm that the GC method couldn't work because it was over 30 degrees. All of these things we solved on our site. We ran this unit actually for almost 3 months. The unit was able to be started up very quickly in Norway. They were able to do a venture capital round very quickly, and they formed the company here, Point Break. I think that's interesting because this afternoon you had the discussion panel here, and one of the questions was around how do you make startups successful or not? And I'm really proud in this case that we were able to help accelerate Norner's desire to enter this market and form a startup out of this project in a very short amount of time. This shows you typically what a naphtha, kerosene, and paraffin fraction looks like coming out of this after it's been cracked extensively. So, successful project in Norway in plastics recycling. Another story I'll talk about today, it's the last one. It says 4. I removed one for time reasons, but I'm talking faster than I thought I was. So if you have any questions, there will be some time in the end. This is the last one. This is a really interesting story about a company called C1 Green Chemistry. C1 was basically kind of born out of the corona pandemic. I found it interesting that the previous speaker also showed data which he was almost forced to generate because you couldn't travel. We had a similar problem here. Basically, the company Creative Quantum is a small company, 2-man outfit. I've known the CEO, Marek, for a long time. They do quantum chemical simulations, and they do it as a service for companies. And during the pandemic, there was a bit of a slowdown in business. So they decided to do some work on their own. And one of the things they decided to investigate was how can we store green hydrogen? Again, in Germany, it's a hot topic. And one of the routes is making methanol out of green hydrogen. So I showed you ammonia before. Methanol is another way to transport green hydrogen. But because they're modelers, they decided to look at homogeneous catalysts and not heterogeneous catalysts. They're much easier systems to model. So what they did is they said, let's see if we can come up with a methanol synthesis catalyst, which has a much lower activation energy barrier to synthesizing methanol, in the hope of being able to do methanol synthesis at much lower temperatures and hence much higher conversion levels, because that's a limitation of current methanol synthesis catalysts, which are basically copper zinc based. To do this, they needed very quickly demonstration unit to prove the proof of principle. We did this in 3 stages. The first one was a very simple one. This was the third one, which was the most complicated one. And the first one was basically a batch. And then the third step here, where they wanted to get from TRL4 to TRL7, they had to demonstrate continuous operation of this. Because the activity of this catalyst is so high, we needed a rather unique reactor. This is a jet loop reactor. The jet loop reactor has a nozzle geometry where basically you're recycling the solvent and the methanol at a very, very high flow rate, adding gas, and this disperses very, very fine bubbles of synthesis gas in the liquid, which means you have a very, very high interfacial area, giving really good mass transport, and you have basically cooling over the entire length of this loop, so you can remove that heat of reaction. You've got the liquid feeding section here. We're dosing a homogeneous catalyst in this case, which is air and moisture sensitive. We're continuously removing the product. We're doing the online analysis with the GC. And basically, they were able to demonstrate the following. And it's an interesting story. If you look at 1923, that's basically when the initial methanol synthesis process was developed. It was developed in Leuna in Germany today. And if you look at the current process now, it's an equilibrium limited reaction. People are typically operating 230 to 250 degrees, somewhere between 30 to 60 bars, depending on what process you're looking at. This is the conversion levels that we're working at right now. What you find that they were able to achieve in this project is to really significantly increase the conversion levels here by being able to go to much, much lower temperatures. Methanol synthesis is an exothermic reaction, and hence lower temperatures favor higher conversion levels. What's also interesting about this catalyst is it makes no water, so it makes product workup much easier. And this continuous unit was able to demonstrate that the catalyst lifetime was significantly long to make it an attractive process for them. So yeah, lower pressures, lower temperatures, are lower CAPEX, OPEX, and a much, much higher conversion. It means you can do the same amount of methanol in a much more compact plant. The idea here is not to make bulk methanol for the market like the mega methanol plants are, but it's actually, in Germany, you have a lot of local green energy being produced, and the idea is you would be able to then have local green hydrogen storage in a container-based system like this. And that's what they're doing right now. They have a container based in Leuna in Germany for this process. And to give you an idea of how we worked together, they had the problem, they didn't have a laboratory. So coming back to the idea of how can companies like ILS help startup companies get started more quickly? Finding a laboratory space in Berlin is hard. It's a big city. So what we did is we converted a whole section of our laboratory to a lab to them. This video shows you they worked with Maersk, big shipping company. That's the guy from Maersk. That was one of the main funders, one of the main VC funders. Maersk is looking at using methanol as a clean fuel. The yellow jerseys that they're wearing are actually the color of the ligand used in the catalyst. So there's actually a meaning to the yellow that they're wearing. You see here we have a glove box installed in our lab, a bunch of power reactors. Basically this is the unit in the back. And this is celebrating really the first liters of green methanol that this unit produced, which was done in our laboratories. I see the music's on. I wasn't going to subject you to that. And we did this collaboration for over 2 years' time until they were able to basically get a lab built for themselves in Germany. They've now moved on to the next investment level, an investment round, and they're still up and going. There are approximately 30 people right now, so they've grown very, very quickly in Berlin. A number of other projects where we're taking the same approach. We're currently working with a company called Spark eFuels. Spark eFuels is looking at chemical looping reverse water gas shift, which was initially invented by these guys. This is Professor Schumacher in Berlin, and one of his students who now works with us on this project. He's an employee at ILS. We'll demonstrate this in our lab. Graham Hutchins, a name I think anybody active in catalysis knows. Graham Hutchins purchased 2 units from us that are still in operation in Cardiff in his lab. One is based around GTL, the other one is around alkane dehydrogenation. Haldor Topsoe has selective hydrogenation units from us, which we first tested on our site before they purchased it. And not too far away from here, we did a really nice webinar with SABIC. I'm very grateful we can mention them. SABIC, this is the SABIC labs at KAUST University. This is a high throughput polyolefins unit. This is probably one of the most challenging units we ever did, where you're doing 6 polyolefins reactors with a robot which is doing all of the catalyst, co-catalyst injections, keeping slurries in suspension, all of this in an inert atmosphere because metallocene, Ziegler-Natta, Chevron catalysts, or Phillips catalysts, they're very air and moisture sensitive. This is a fully automated unit which has been in their lab for roughly 4 years now and is just about to move to Geleen in the Netherlands. So all of these are examples of clients who have chosen to do the chemical validation in our laboratory before we sent the units. Yeah, with that, I'm at the end of my presentation. I'd like to thank KFUPM, in particular Dr. Wael and Dr. Atiani for having us here and also for trusting us with the project that we're currently doing with them. And thanks also in the name of everyone from ILS. This is most of the team. It's impossible to get them all there on one day. Yeah, and thank you for your trust. Thank you for listening. And nobody fell asleep, so that's a good sign. Yeah, thanks.
Thank you, Dr. Anton. We have time for one question, please. Microphone.
Your microphone's coming.
Thank you. Great talk. I'm just wondering about the time scale when you receive a problem, and then you start to evaluate it, and then you start to execute the procedure. So can you give a snapshots about this timeline?
Did you pick propylene because you're particularly interested in the polypropylene?
No. In general,
okay.
On average, yeah.
Yeah. It really depends on the project. So, like I said, the ammonia cracking project. That was fairly quick. I think that was about 2 months that we did it. I'll be honest with you, it takes almost a month just to get the GC calibrated and kind of get a baseline. So chemical validation less than a month isn't possible. Because it was challenging but not really, really hard, 1 month of testing was sufficient and we were done with that project. With the polyolefins example that I showed that we did for KAUST, I think that thing, it was roughly 6 months in our lab. There are only 2 other units like that in the world, and they were made by a company called Symix that doesn't exist anymore. So it was, like I said, one of the most challenging units we ever made, and hence it really took a long time. And I think one of the real keys to success in that project was it was collaborative. Yeah. So it's not like the client orders and then we lock ourselves in our laboratory and we just start testing things. SABIC, the team of Mark Flahr and Nick Friedrichs, they're some of the best polyolefins people in the world. So it was really, really important that we had a very close interaction saying, hey, look, we're seeing this, we're seeing this, we're seeing this. They would put together a DOE with us, which we would then execute, and they would then evaluate the data together with us to help us basically understand at a much more fundamental level what we're doing wrong. And with a thing like that, 50 milligrams of air and moisture sensitive slurry injected into a half a liter vessel reproducibly over and over is actually, it's not trivial. And that was one of the biggest things we were confronted with. A number of other things as well. But very collaborative is basically what I'm saying. So 2 months to 6 months, worst case, yeah? It's definitely cheaper than it being done on the client side, because as I said, they're not burning through their own OPEX and CAPEX. Sorry
Thank you,
for
Dr.
the long
Anton.
answer.
That was very great
Yeah.
job. Thank you
Yeah.
very much. Highly appreciate it.
Thank you.
It's again my great pleasure to introduce our colleague, Dr. Thijs Solling. Dr. Solling is currently a senior research scientist at the program lead of the oil field chemistry program in the Center of Integrative Petroleum Research at the College of Petroleum Engineering and Geoscience at KFUPM. He obtained his MS in chemistry in 1997 and PhD in 2000 from University of Copenhagen, Denmark. Then he did his postdoc research under Nobel laureate Ahmed Zuhail, Allah yarhamu, at Caltech, focusing on ultrafast spectroscopy and reaction dynamics. Dr. Solling subsequently worked at RISO National Laboratories in Denmark before returning to academia as an associate professor at the University of Copenhagen, where he investigated ultrafast process in organic chemistry. I think if I want to continue, I will probably take more time. But I would like please to join me to welcome Dr. Thijs Solling for his presentation. Thank you.
Thank you so much. That was an elaborate introduction. Appreciate it. So this is the just test. Great. Okay. Very big auditorium. I'm kind of humbled to be here. Luckily, not luckily, but the concentration of people is not that big right now, but it's also lagging towards the end. So I'm appreciative to be able to address you with this little problem that we have found out of doing, as we do in CPG, fundamental studies with a line of sight towards application. So this came out of an interest in looking at oil field chemistry relevant molecules, the Gemini cationic surfactant that we have developed in our own laboratories. That's the part that's headed by Shakil Hussain, who's also mentioned here. And we were interested in initially see or look into the speciation at an interface of water and air to address what would be the sort of distribution of molecules at an interface from a production of surfactants that's sort of a mess, because sometimes when you're doing oil field chemicals in a commercial setting, you cannot necessarily get the pure compound. So we were working on distributions of molecules, and we were interested to see whether we could sort of tweak one of the most surface active components to move to the surface or to the interface. But then, as I said here in the first slide, basic research to application, that was the application, and the study led to some pretty exciting fundamental discoveries. As we have seen earlier on by the talk from Professor Seher, and also to some extent by the talk of Morten Meldal, interfaces are becoming increasingly important. There are chemistries that are playing out at the interface that are triggered by the interfacial properties, the specific charges, the highly charged species that accumulate at interfaces are sometimes triggering reactive environments that we haven't necessarily seen before. Of course, other than that, in the oil field domain, interfaces are where the most predominant properties are determined. These are the domains where we are focusing mostly to impact the properties of oil and gas reservoirs to be able to produce better from oil and gas reservoirs. And that's primarily what all the surfactant chemistry was designed towards. So it's relevant in EUR, it's relevant in interactions with brine, it's relevant in demulsification, everywhere in the oil and gas sector. And now I'm going to lead you to a little bit of a different direction and try to explain what we did to study the interfaces. And that is something that I did in collaboration with Jack Beecham at Caltech. He developed a method which is called field-induced droplet ionization, also in abbreviation FIDI. And to a large extent, what we are trying to achieve is to impact a droplet in an electrical field so that we are sensitive only to, well, I mean, it's an exaggeration to say the first few layers of the droplet, but at least more sensitive to the interface, to the speciation and the chemistry at the interface than to the bulk. So that's what this is about. I won't go into any of these equations or further elaboration on how it works, but the essence is that this FIDI method will enable us to study species at the interface. Now this is what the setup looks like. It's a home-built setup, which is essentially just put in front of a triple quadrupole instrument. So I'm not able to point, I don't think. Oh, I am. Excellent. So that is the inlet of a commercial mass spectrometer. So slightly modified. Essentially what we did was that we took off the regular ion source in front of the front end of the instrument and built our own source, which is where this elongation of droplets takes place in a high field. It's pulsed so that we are able to supply a pulse in a certain time, open the mass spectrometric analysis, and look at what came out of that pulse. That's what the field-induced droplet ionization does. So the picture in the middle is the ion source. These two plates are biased, so a very high voltage on one of them and ground on the other one, and that is then inducing this elongation of the droplet. So the droplet is hanging, and we are studying the chemistry of the interface of that droplet in this field-induced droplet ionization mass spectrometry setup. So I thought I wanted to show you a video of how it plays out. I wonder if I can play it myself. I can indeed, I think, yes. So that's now the hanging droplet, and that was the trigger. Hope you saw it. Maybe we can go back and do it once more. So the droplet is hanging there. I manually press a button that initiates the field between the plates, and then the droplet elongates, and essentially the aim is then to peel off the first few layers of the droplet and feed it into the mass spectrometer and do the mass analysis and thereby characterize what is on the interface. So here, the pulse, and that's essentially how the method works. So it's all done in a hanging droplet setup. I was also working towards trying to do merging droplets, but that hasn't been fully developed yet. And there are, of course, all sorts of caveats in this technique. You can argue that the needle might be triggering reactions, and you can argue that what you see is impacted by the inlet of the mass spectrometer. So there are some things to be taken into consideration. But nevertheless, I think the results that I'm going to present to you right now are reasonably clear-cut in making a statement that goes towards the highly selective environmentally, or the highly selective environment, or reactive environment that we have on a hanging droplet. Now, I don't need to put too much effort, I guess, into summarizing the relevance of surfactants in the oil field domain, at least. Shaquille's team has developed these surfactants so that they are resilient at high temperatures, which is one of the challenges in Saudi Arabian assets. The reservoir temperatures are on the order of 120 degrees. So that's one thing. And it has turned out that these Gemini cation surfactants are pretty good at that. In addition to being resilient to the high temperature, they're also resilient to high salinities, not only from an angle of decomposition, but also from an angle of precipitation. That's why we have pinpointed these, and again, we were interested in seeing how they distribute themselves at a water-air interface. Now, they don't come clean. The industrial applications sometimes warrant low cost, or oftentimes that's essentially always the key when it comes to a chemical technology. It's always about upscaling and price. And we're not able to generate or to make these particular surfactants in a cheap way, while at the same time having them as a single molecule constituent. So it's a mix, primarily a mix on the distribution and the composition of the side chain in these Gemini cationic surfactants. I'm going to show you some structures in a short while. We were, of course, interested in characterizing these synthetic products. And as you can see, this is a regular electrospray mass spectrum, and there are a whole lot of peaks, and it very clearly, or very early on, became evident to us that this was a bit of a quagmire to molder into and to try to unravel. The distributions that you can sort of see in the mass spectra, you can sort of see that this is like one distribution of molecules with the center point being 724. Here are two other peaks that are forming the basis of a distribution, and the 980 is forming another basis of the distribution. And the distribution is due to the different number of ethoxylate units in the Gemini cationic surfactants. We cannot make only one specific side chain, so they have a variation in the number of ethoxylate units. So that's why we have these distributions. But in principle, it should be only one distribution. And what we came across in this electrospray ionization is that it's actually 4. And that was already a little bit puzzling. But we managed to figure out why that was. And the claim here is that the parent molecule, the surfactant that we are making, weighs around 1,600 grams per mole. Now then we should see only one distribution anchored around this, around 1,600 grams per mole. But we see these 4 at a lower mass. So that can either mean that since the Gemini cationic surfactant is doubly charged, it could mean that it's at half the mass, but that's not really the case. We don't see anything at exactly 800. We see them either lower or higher. So we attributed it to a decomposition which is highlighted here in this slide. And there are actually 4 ways that this molecule can break if it does it in a heterolytical manner and still retain the charge in either of the fragments. And it actually matched pretty well with a rupture right here, and a rupture then also leaving the positive charge in the other side of the molecule. And then also we have a homolytical rupture, which leaves us with radical cations. So these 2 decomposition patterns matched very well what we saw in the electrospray mass spectrum. In the regular bulk setup, electrospray essentially ionizes the bulk. So you see the property of what's going on in solution. Now, since we were interested in looking at the distribution at the interface, because it's surfactants, we are interested in how they place themselves at the interface being surfactants. We did an experiment with this interface sensitive mass spectrometry method, the FIDE method that I just went through. And interestingly, we saw 2 phenomena. Very shortly after dispensing the droplet, doing an ionization trigger led us to a spectrum that looks like this. A high-end mass distribution and a low-end mass distribution. Leaving the drop hanging for a little while, we end up with what is essentially the same appearance as in the bulk setup, the electrospray, similarly oriented mass spectrum. So now, doing the mass spectrometry with an interface-sensitive method revealed a molecular mass that is actually close to the mass of the molecule itself. So for some reason, it doesn't decompose. But there is more to it, because remember, it was a Gemini cation exsurfactance, so that means 2 charges. That means in mass spectrometry that you're looking after masses at half of the mass because you divide by 2. So in mass spectrometry, you measure the mass to charge ratio, and since the charge is 2, you're looking into half of the mass. But that's not the case here. And there is really only one way of explaining that. And that is that the Gemini cation exsurfactant is now no longer a Gemini cation exsurfactant, but a species with only 1 charge. And how can that play out? Well, that can only play out if it has an extra electron at the nitrogen. So this is the first example of a so-called hypervalent nitrogen species formed specifically at the interface. So I put it down here. This is what it looks like. So this is the quaternary ammonium ion entity of the Gemini cation exsurfactant. If it gets an electron, now is my time up, or no, it's not up. Great, we're back. If it gives an electron to the quaternary ammonium site, now we are ending up with a nitrogen which has this extra electron, which is now violating the octet rule. So that nitrogen has 9 electrons around it. That's a no-go in chemistry 101, right? No second period atoms will ever violate the octet rule. But nevertheless, when forming or when decomposing these Gemini cation exsurfactants at the interface, we form species that does exactly that. And of course, that's not a favorable situation, so it's a highly reactive molecule, and these molecules, hypervalent nitrogen species, are previously observed to have lifetimes on the order of microseconds. They are observed in the thin dilute gas phase with lifetimes in this range, but I'm talking here in minutes. So we have been able to generate a method that forms these highly reactive hypervalent species interface specifically with lifetimes in the order of minutes. So we thought, of course, that was pretty exciting. And now, of course, the remaining question is, why on earth is that possible? I came up with an explanation highlighting exactly that. This is just to show you that as opposed to the electrospray experiment, the reactivity pattern here is really in a single direction. So it's pretty specifically induced by the hypervalent nitrogen as opposed to in the bulk where there were these 2 different channels. But now, since we are inducing a very reactive site, that will trigger the subsequent reactivity. So the reason why I'm saying this is that we are only seeing peaks that are spaced by this 44, which is the ethoxylate unit, and 16, which is an oxygen. Nothing really sort of other than that, meaning no other reactions. This is just a distribution that's caused by the original provenance of the molecule in place. So why? And I think Professor Sayer highlighted this already in his talk very nicely. There are certain aspects of the interface that are not conventional in the way that we think of bulk chemistry. There are charges that are pretty extreme. There are solvation environments that are very odd, very, very different from what we are used to. And the solvation environment in particular is what I think is in charge of this specific reactivity. So what we're dealing with here is rather than in the bulk having this Gemini cation exsurfactant with its counterion, which is a bromide, in the bulk it would be normal to think of a solvation process where the bromide ion is leaving the cationic site to be surrounded by water molecules. Regular solvation of a salt. At the interface, there's no space for that. particularly since we have these long entangled chains from the polymeric surfactant that leaves really no room for water molecules to percolate into the, what should I say, membrane structure to solvate the bromides. So rather than heterolytically displacing itself, the bromide homolytically cleaves off from the nitrogen side and renders the nitrogen with an extra electron. So this specific highly packed environment is what gives rise to the hypervalent nitrogen. What happens then to the bromide? Well, the bromide becomes a bromine atom, and the bromine atom will find another bromine atom and essentially form a bromine molecule, or do something else with which percolate out and react with a water molecule or whatever. But fact of the matter is that when doing the energetics in an ab initio calculation, in a pretty simple-minded one, it is actually energetically favorable when you take into account the subsequent reactivity, the subsequent decomposition, to take this reaction route. And the image on the right-hand side is a molecular dynamics simulation where we also try to validate the distances between the bromine atoms to show that this is the most favorable phase of the bromine rather than solvation. There's really not much space for water. So what can we use this for? Why is it at all relevant? Well, if it's possible to design a polymeric interface, a polymeric-oriented interface that has these properties, then we can maybe make highly reactive species that are relevant to aerosols, that are present at aerosols, that can be used as chemopharmaceutica in some way, shape, or form. At least I have shown here that the interface is a playground for forming highly reactive species that potentially can play further out in other reactive pathways. So with that, I would like to thank you for your attention and for staying awake.
We have time for one question, please. Microphone, please.
Thank you so much for this lovely talk, an exciting talk. What I going to tell you, speculate to you, is that if you'll look, you'll see HOBR. Have you tried that? Because I really think that's what will happen. Your bromine radical and your OH radical recombine.
Yeah, I think you're right. That would be the right place to look. Unfortunately, I didn't look below Mars 150. And the nature of this study was one of these, similarly to what Bashir has been doing with you, a summer study abroad. So I'm thinking about building this source in KPPM as well. It's not that difficult. It's a couple of plates and some electronics. The challenging part is to do the triggering of the high voltage. But that would be an obvious place to look, or somehow spectroscopically as well. Try to characterize the bromine. Thanks.
Any other question? Okay, thank you. Thanks. Okay. مسك الختام. It's my really honor and pleasure to introduce my neighbor, Dr. Joy Tannous. Of course, why is my neighbor? This is takes a long time to explain. Dr. Joy Tannous is an associate professor in the Department of Chemical and Petroleum Engineering at the United Arab Emirates University, Al Ain, UAE. where she engages in cutting-edge research in the interface of material science, petroleum engineering, and environmental chemistry. Her research profile is especially notable for investigations into free radical chemistry, asphaltene behavior in heavy oil, ionic liquids, aerogels, and biomass conversion, demonstrating strong material engineering orientation applied to energy and sustainability challenges. She graduated with a PhD from University of Alberta, Canada in 2019. Then she continued as lecturer and postdoctoral fellow at the same university before joining the UAE. Dr. Tannous' scholar influence is reflected by her high H index and citation metrics. Please join me to welcome Dr. Joy Tannous in her presentation.
Assalamu alaikum. Can you hear me? I'm so short here. Okay, good. Great. So this is Joy, and I'm coming from the UAE University. Today, actually, I will not be talking about a single experimental study, but rather, let's say, overview of the outcome of several work we've done on free radicals. So I will be talking about the factors affecting free radicals in oil upgrading processes and also in oil storage. I will start with a quick background, how the story started, how I got interested in free radicals. And then I will have a quick overview on free radicals in oil upgrading. Then I will elaborate a bit more on free radicals stability upon storage, because this is the topic that we're currently working on and trying to understand. I'll start first with the background, how the whole story started. Actually, I was working at the University of Alberta with heavy oils, and we wanted to actually transport heavy oils in pipelines, either for further upgrading or for the final user. So for that, we actually had to crack it and decrease its viscosity. However, when trying to crack heavy oil, we were forming some asphaltenes, which are heavier compounds than the feed, and this was not desirable at all. So while we were trying to understand the asphaltene formation during the cracking of oil, I started introducing some different compounds to see how they affect the formation of the asphaltenes. And one of these compounds was indene, actually. And then I ran a control experiment in which I reacted indene alone. So I just put indene in the reactor. And I got some indene here. Yeah, so I got some indene, some cracking products, addition products, but also asphaltenes and a lot of asphaltenes. So you can see here, actually, I started with something like this, as light as this, and I got 72% of asphaltenes under 400 C and 2 megapascal and nitrogen. So I started wondering, actually, what could be the reason for this. And then I realized there is what we call the molecule-induced radical formation, which is something indene is capable of. And indene, in that case, will form actually a very stable free radical that is stabilized by both allylic and benzylic positions, and will start performing addition reactions and forming asphaltenes. And that's where the whole story started. Now I'll just go a step backward just very quickly to introduce free radicals in case you are not familiar with the topic. So the understanding of free radicals for general public is mainly things that cause cancer, and this could be actually the case because the study on free radicals in biological systems and the human body started like very long ago. But briefly, free radicals are just species that have an unpaired electron, and they are very important in various processes, including polymer synthesis, geology, which includes the geological formation of petroleum and so on, thermal processes, anything that requires temperature, in the human body, obviously, in oil stability, polymer degradation, and so on. For example, in our human body, there are a lot of free radicals, and the origin is mainly from the metabolism, the cracking of the food we eat, from the smoking, exposure to either UV or ionizing radiations, and from air pollution. All these causes free radicals to penetrate our bodies, but luckily we have antioxidants that can quench these free radicals. However, if the amount of free radicals that we have in our body is higher than the amount of antioxidants, then we will have an issue, and because free radicals will start attacking actually healthy atoms. So they will try to grab an electron from the healthy atoms, and they will cause some damages to them, leading to several diseases. So how do we know how much free radicals we have, or how do we detect and know the amount of free radicals? This is by what we call the electron spin resonance spectroscopy, or the electron paramagnetic resonance, which consists of just putting the sample in the. In our case, we use this Magnetec ESR 5000 model, and we have a peak if we have free radicals. I will briefly go through this because I know time is very limited, so I will go briefly through this and then I will elaborate on the other section. Free radicals in oil upgrading, as I mentioned before, the whole story started with the heavy oils. So in order to crack these, we actually go through a free radical mechanism, but the problem is not only in the creation of the free radicals inside the reaction itself, but also the heavy oil itself contains inherently some persistent free radicals, heavy oil and other unconventional sources. So that is the main issue. So when we undergo thermal cracking, we are forming cracked products, but we are also forming some asphaltenes, which are due to some free radical addition reactions. So this is the free radicals adding to each other and forming larger molecules than the feed. This is not the aim of this unit. The aim is to crack molecules. So the main challenge was actually to favor cracking over addition reactions. And this is how free radicals are relevant in oil upgrading. When we were trying to quantify free radicals, we realized that the quantification of free radicals is actually not established in the literature. So we also published this paper on the quantification of free radicals in different oil sands bitumen fractions, and we noticed that they are, as I mentioned before, they were inherently present in many of the fractions, which already created a lot of issues in the processing of these fractions further in the refinery. Let me elaborate more on free radical stability upon storage. When I was a student, I was thinking that if these free radicals are inherently present in my oil, then this oil is being stored maybe sometimes in different conditions, different temperatures, and for different periods of time. So how is these free radicals present stay the same throughout all the time and all the factors of storage? So I decided to start working on measuring this stability. And here we have found that I tested maybe 54 solvents here on a single analyte, which is bitumen. And I found here only showing 3 solvents, already showing a shift in the peak and different peak sizes as well. So I decided to change the matrix because honestly it was very difficult to understand the chemistry and what's happening in a matrix as complex as bitumen, which we cannot even draw in a single molecule. So I decided to shift focus towards more simple molecule, and which is DPPH, which is a very known persistent free radical. It's a very stable free radical. So we worked on DPPH and we did here a bunch of studies. We studied the impact of storage time, the impact of different solvents, and the impact as well in this paper of the storage temperature. So we stored it at room temperature under fridge conditions, freezer conditions to see whether this free radical stability is modified or is changed. We basically dissolved around 0.98% of DPPH in different solvents. Now, why 0.9? This is another story. We can takes more time to discuss. We can maybe discuss it if you after the presentation. So we studied, as I mentioned, the storage time, the solvent, the temperature effect, storage temperature effect. And we already see different peak shapes with different solvents. And again, this is the same molecule, but with dissolved in different solvents. So we're seeing different peak shapes. And even we found that some of the solvents might affect actually the G factor. What G factor means the free radical center or type of the free radical that we have. So for example, here I'm just giving an example. In the case of THF, for example, we saw some a shift in the radical center to the carbon, so from nitrogen to carbon. Other examples like hexyl benzene, which might have capped the free radical here. And methyl naphthalene, for example, just very quickly, I don't want to go through all the details of this. So the methyl naphthalene, for example, it was lead to a shift into an anion here instead of a free radical. Another thing we've done is we see the effect of how the free radicals initially, if we store them at room temperature, what happens actually to our number of spins. Spins means the number of free radicals. So you can see here with tetraline, it's a very well-known hydrogen donor. We can see already a sharp decrease in the free radicals, 99.6% weight percent decrease in the free radicals. For toluene benzene and diphenyl sulfide, it was more relatively stable with percent changes, lower percent changes in the free radicals. And THF, methyl naphthalene, mainly very high decrease in the free radicals. This is upon storage at room temperature for a period of 3 months, this study we did. So, long story short, we noticed actually there are a change in the free radical with different solvents and to different states of the DPPH, for example. And this leads actually to different colors. We were able to distinguish also the colors, and the pH was also changing. Like we have the anionic state, the hydrazine, or the hydrazine radical, which is the initial state of that radical. And this is depending on the type of, so it's due to the solvent's hydrogen or electron doning ability, which converted to free radical to the neutral or to the anionic form. The second study I mentioned, this was about the effect of temperature. So this is, we stored at fridge and freezer. We can see a better stability, but not for all solvents actually. So you can see here for electron donating solvents, we had a large improvement. Now the decrease in free radicals is only 24 or 8% compared to 99% at room temperature. But for hydrogen donating solvents, actually there was no improve in the free radical stability over time. We've done also other work. I went back to oil here. So we did the same study, but on oil, because I really wanted to understand what's happening to oil at different solvent, different storage times, and different storage temperature. This is very important for free radical processes or processes that will use the oil to crack it or to undergo any free radical reactions. These are other works that we've done also on free radicals. But in the future, I plan to, so oil stability, actually thermal processes, I'm already working on these, but in my research group, we plan to expand a bit on the use of free radicals. We're trying to shift a bit towards the environmental impacts and mainly environmentally persistent free radicals. Maybe a bit about also food safety. I'm a bit interested in frying oils and biomass. I would like also to acknowledge a few people here, the United Arab Emirates University. Here you can see me with, this is Professor Arno de Klerk, my supervisor in the PhD, who also happens to be also the supervisor of Dr. Muhammad Siddiqui here, your colleague in KFUPM. Also, this is Dr. Lina Janiez, which also we happen to publish a paper together. This is my research group, not fully. In the UEU, that's the only photo I have. I should take another photo with all of them. And this was a very, very nice time in 2023 where I managed to meet Professor Gareth Eaton and Professor Sandra Eaton. These are the big names in free radicals, and it was a great honor to meet them in Denver University. Anyone that wants to do any quantification of free radical, they will refer probably to their book, Quantitative EPRs, which is very, very popular. Thank you all for your listening, and if you have any questions, please feel free. Thank you.
Thank you, Dr. Tannous, for a very interesting presentation. Please, we have time for a couple of questions, if any.
Yeah, thank you for your talk. I was just wondering about if I get your point quite well. You're saying that in the crude oil, we do have a radical that can, how these radicals are stable in the oil upon interaction with water, for example, and other minerals in the reservoir. And so can you just elaborate on this?
Yes. Geologically, in the formation of petroleum, we will have free radicals due to the formation of kerogen. But if you're referring to the light oil, you will most probably not find much free radicals. This is mainly in the heavier fractions of the oil. And yes, it is inherently there. For example, in what I was working, oil sands bitumen, we have interaction with the sands. We have later in the assisted gravity drainage, they add also some water. So yes, there might be some of the radicals that are interacting with water or other environments around. It depends on which processing we're doing. But there are a large number of persistent free radicals. It's in the range of, if you have noticed here, in the range of 10 to the power 18 spins per gram. Of free radicals, and these are persistent free radicals, most probably sterically hindered. Maybe they cannot be reached to interact with anything at all. Some of them are not sterically hindered. They are just persistent. They have very long lifetimes. We don't know chemical structures for these, like we cannot really draw structures yet for the oil. That's why I shifted to simpler matrices, trying to understand what's happening in there. But yes, they are there. I hope this answers the question. Thank you. Thank you, Prof.
Any other question? Okay, thank you, Dr. Joy. It was a very nice presentation. Thank you. And by this, we announce the closure of this afternoon session, and we will see you tomorrow morning, inshallah. Okay, thank you for attending this session. Good night.